All right, section 7, introducing the TCP/IP internet layer. Internet layer, of course, is layer 3 of the OSI model. So what are we going to talk about in this layer? We're going to talk about IPv4 addressing. We're going to talk about subnetting. We're going to talk about potentially routing as well, and actually quite a bit in this particular section. So we're going to start now to kind of get away from some of the basic concepts that we've been talking about the last couple of days, and hopefully we'll start to get into some more of the advanced concepts that you guys will, you'll have an opportunity to learn a little bit more about as part of this process. But when we talk about the internet layer, we're really talking about the routing of datagrams, moving datagrams from one subnet to another, from one broadcast domain to another. And that's what our focus is going to be on. So in this section, we're going to talk about what is IPv4 addressing, what are the general addressing characteristics of IPv4. We're going to talk about IPv4 address representation, the structure of IPv4 addresses. For example, what is the network portion of the address? What is the subnet portion of the address, the subnet mask? What I like to refer to as the prefix and the prefix length. That's a typical term, or those are typical terms that we use to describe IP addressing. What are the address classes? We don't really deal with classes too much these days anymore, but we did start with classes: Class A, Class B, Class C, Class D, and Class E. So we'll talk about those. We'll also talk about different types of reserved IPv4 addresses. That should actually say IPv4 there, but we're going to talk about different types of reserved addresses, things like loopback addresses, the Ipv4 address range, the 169.254 address range. We'll also talk about what is a network ID, what is a broadcast ID, and then we're going to take a look at subnetting as well, and what variable length subnet masking is. And of course, we're going to do quite a bit of subnetting calculations. There are a couple of questions on the test related to subnetting. They're not direct subnetting questions per se, but there are a couple of questions on the test about where you have to, in fact, I added a drag and drop this morning that's a subnetting related drag and drop that I saw in the groups last night. So we will talk about that. And then finally, we'll do our discovery. How do we verify IPv4 settings on an end host? That's a pretty basic concept. We're talking about things like ipconfig and so on. So what is the internet layer? With regard to the TCP/IP stack, the internet layer is layer 3. A lot of things happening at this layer. Of course, we have our transport protocols like IPv4 and IPv6, and we're going to spend a lot of time talking about IPv6. That's going to be something that's probably relatively new for you guys. Routing occurs at this layer. Packet delivery occurs at this layer. So we're going to spend a lot of time talking about those concepts as well. Those are really actually very important concepts that we're going to be discussing. There's some basic characteristics about IP in general. Number one, the layer is connectionless. What does that mean for the layer to be connectionless? It means that there's no guaranteed delivery of data. There's nothing in a V6 header. There's nothing in a V4 header. Routers don't have natively built into them the idea of sequencing and acknowledgement. So the packets that are delivered at this layer, layer 3 of the OSI model or layer 2 of the TCP/IP model, means that we send these datagrams, and even though the datagrams might be part of a flow of information, they're treated independently. There is something within IPv6 called a flow label, which could potentially be used to identify packets in a flow, but basically the way a packet is treated is it's treated independent of any other packet, even though it might be part of an overall processing, overall flow of information. All right? So every single packet is going to be treated independently. That's a good thing, but it can also be a bad thing because it means that each packet has to be analyzed separately, and we have to process those packets separately. But we could do some things like marking of packets that would allow us to identify potentially that packets might belong within a flow. What do I mean by that? I've said that term a couple of different times. What is a flow of data? A flow of data are the groups of datagrams that are related to each other, right? If I go to a web page and I open up a web page, I'm not just gathering that information with one packet. I'm sending multiple packets back and forth, and those packets are related to each other. And one of the things that we'll talk about today is the transport layer and how we manage that at the transport layer as well. We're going to talk about the hierarchical addressing structure as well. Within a subnet, within a broadcast domain, we have a range of IP addresses that we can use to communicate, but some of those addresses have very specific purposes. Like the very first address in IPv4 and IPv6 is called the network ID. And that allows us to identify the network that you belong to. That type of address is an address that's used by routers, for example, to build the global routing information base to be able to identify what networks exist and so on. All right, best effort delivery, no guaranteed packet delivery. Packets could be duplicated, they could be redirected, they could be lost. There's nothing within the IP header or IPv6 header that guarantees or at least allows us to identify that that packet was misdirected or lost or otherwise not delivered to the destination. The other thing about IP, unlike the link layer, the data link layer or the link layer in the TCP IP model, we are completely independent of the transport. What I mean to say is at the data link layer, you wouldn't be running Ethernet over a serial link. Conversely, you wouldn't run HDLC or frame relay over an Ethernet link. So the physical medium that you have at the link layer or at the physical layer will determine to an extent what type of protocol you run at layer 2. IP doesn't care. IP runs over frame relay, it runs over Ethernet, it runs over ATM, it runs over X25. All these other protocols, we don't care what the underlying transport is. We don't care what the underlying physical transport is. IP is just IP. All right? There are some, in the history of IP, there's been many different types of IP, or at least types of network layer transport protocols. IPX, Internet Packet Exchange, AppleTalk, but predominantly what we use today is IPv4 and IPv6. So we're going to spend a lot of time talking about those two protocols. We'll do Wireshark captures. We're going to look at the packet headers. We're going to break down the packet headers for each of these bit by bit, basically, so that when you look at a Wireshark capture, you know what's happening within that processing of that particular datagram. So one of the things, obviously, that you're going to have to be somewhat familiar with, and we did a little bit of discussion about this yesterday, is you're going to have to understand the relationship between decimal notation, for IPv4 at least, and binary notation, right? We know that we write our IPv4 addresses in dotted decimal format. They're 32 bits long, and they're broken up into what we call octets. 8 bits each within each of those 4 octets. The first octet being the far left octet, the second, the third, and the fourth. All right? So they talk about, for example, in the book here, 168.10.22 is the binary equivalent of this string. Now, I always get my students always kind of say, well, I don't really need to know how to do these conversions. Because I can use a calculator, or I can just use Google or whatever to search on a conversion factor or whatever. But the reality is, the better you get at recognizing the different numbering formats, hexadecimal, decimal, binary, the better you will be at troubleshooting, the better you will be at understanding really kind of how things function. I'll make a point of this. When I'm going through the demonstrations this morning, I'll make a point to demonstrate what I mean by quickly being able to recognize different number formats and how that can really benefit you. All right, so let's go ahead and just do a quick review. The book doesn't really get into it in a lot of detail here. All right, so what we're going to do is just kind of a quick review again of the binary representation. Again, as we talked about before, we were talking about the powers of 2 scale, the radix scale, if you will. Now, the number of binary bits that you need, in other words, the length of the field or the size of the binary field is based on the decimal value that you are trying to represent, right? And that's actually a very important concept, because when you look at a Wireshark capture, for example, and you look at various fields within the Wireshark capture, you're going to notice that some fields are 16 bits, some fields are 4 bits, some fields are 1 bit. Those are called flag fields. And again, what you can, the information that you can contain within that field is going to be based on the size of the field. For example, a VLAN ID field in an 802.1q tag. That is a 12-bit field. So that means mathematically you can only have VLANs from 0 to 4095. You could never have a VLAN above 4095 mathematically because it's just a 12-bit field. Does that make sense? Same thing applies to, say, for example, the port number field in a TCP header. Those fields are 16 bits long or 16 bits wide. So that means that you can only have port numbers 0 to 65,535 because 2 to the power of 16 is 65,536. So understanding the size of fields within the headers, understanding how many bits they represent, gives you a good indication of how that field can be utilized to represent whatever information it's trying to represent. So for example, a TTL field in a packet header, as an example, is an 8-bit field. So that means mathematically 0 to 255. All right, now what does that mean on the powers of 2 scale? We've got 1, let me do this way. 1, and I'll just copy that. 2, 3, 4, 5, 6, 7, 8. 2 to the power of 0. 2 to the power of 1. We did this yesterday, but I'm going to do it again because I want to make sure that you guys understand this. 2 to the power of 2. 2 to the power of 3. 2 to the power of 4. We get there. We only need to go up to 7. So 2 to the power of 5. 2 to the power of 6. And finally 2 to the power of 7. There's really no limitation as to how large this binary string can be. It could be 32 bits, and in fact there are some fields like sequence fields and acknowledgement fields in a TCP header that are 32 bits wide. But here's a good point, right? EIGRP named mode. We talk about that in our advanced routing class for CCNP. EIGRP named mode uses a 64-bit wide metric, okay? Regular EIGRP classic mode uses a 32-bit wide metric. So when they designed EIGRP named mode, they had to put in something called a RIB scaling factor, because when you took metrics from routes in EIGRP named mode and you tried to put them into the global routing table, they wouldn't fit, because the global routing table field for the metric is smaller than the metric field for EIGRP routes in the EIGRP RIB. So you're going to see this as you continue with your career and you start to get into more and more advanced concepts. Understanding the relationship between the size of fields and how they're represented in binary and decimal and hex really is very useful in understanding how protocols work, why certain things are done the way that they're done, and it's just really, really useful, okay? So you have this powers of 2 scale, and again, I just did 8 bits because I was specifically referencing this time to live field. And then each one of these fields, or each one of these columns, if you will, have a decimal weight. This has a decimal weight of 128, and this is 64, and this is 32, and this is 16, and 8, and 4, and 2, and 1. All right? So if you were to add up all those numbers, 128 plus 64 plus 32 all the way down to 1, guess what you would get? you would get 255. That's the high end of the decimal value of 8 bits. The low end would be if all the bits are 0. Does that make sense? So again, and we'll see this. I mean, guys, I'm harping on this, and I apologize for that, but even with like VLANs, right? When you, or a spanning tree, excuse me, when you talk about spanning tree, which is part of your self-study section, we talk about something called the bridge ID, all right? And Cisco, when they implemented spanning tree, they went to an extended system ID format. They took a 16-bit or a 2-byte field that usually represented priority in a normal bridge ID format, and they broke it up into 12 bits and 4 bits. But they didn't change the numbering of those, the weight of those columns, so now you can only set priorities with the extended system ID format in increments of 4096. And again, all this has to do with understanding that relationship between this, what we're drawing here, this binary scale, and how it's used in the protocol. So I don't care if you understood specifically what I was talking about with the extended system ID, but my point is that you're going to see this over and over again. This is not just for subnetting. This is for all kinds of number representation. All right? So, and I know that you guys probably know this already, right? To represent any decimal number, you simply turn on the bits that add up to whatever that decimal number might be, right? The value of that decimal number. So for example, I've got 128 plus 32, which is 160, plus 16 is 176, plus 4 is 180, plus 1 is 181, right? Wherever there's a 1, you're going to include that as part of the weight. So we're going to say in this particular case 128 plus 32 plus 16 plus 4 plus 1, oops, plus 4 plus 1, and that equals, what did I say? I can't remember now. That equals something, right? 128 and 32 is 160, 176, 180, 181, all right? Eventually you get to the point where you kind of start to recognize some common numbers, because there's a lot of common numbers that you'll see. But again, the base is important, right? And we use a powers of 2 scale to define that base. And it's all about the position of the 1 or the 0, which allows us to determine the decimal value. Decimal obviously is a base 10 system, but we're using this scale, this powers of 2 scale, to represent these various numbers, all right? And they go through an example in the book here. Specifically, they say, well, okay, so 27,398. Now, if I'm looking at 27,398, I'm immediately thinking in my head powers of 2. So I'm thinking, okay, it's got to be higher than 16,384, which is a power of 2. That's 2 to the power of 12, I think. So 7 is 128, 8 is 256, 9 is 512, 10 is 1024, 11 is 2048, 12 is 4096, 13 is 8192, so 14 is 16,000, whatever I said. Now I lost my train of thought. But basically I'm just doubling it each time, right? Each time I go up a power, I'm doubling the number. 16,384 is what I meant to say. So I know I would need more than 14 bits to represent 27,398, because 2 to the power of 14 is 16,384. 2 to the power of 15 is 32,768. Okay? So I know that I would need at least 15 bits to represent that number. They kind of do it a little bit differently here, right? They're kind of breaking it down into tens, right? Powers of 10, so 10,000 plus 1,000 plus 100 plus 10 plus 8 times 1. But if you were to apply that to the powers of 2 scale, it would require 14 bits. I'm not going to do this method because it's this isn't even really, I guess it's kind of the powers of, it's not even really a powers of 2 scale. It's a little confusing actually. All right. But the binary system, of course, we only use zeros and ones, so we have to simply represent these positions within the string of binary numbers and apply this decimal weight to those positions. Remember how yesterday I stated that each hexadecimal character, each hex character is 4 bits, right? Well, there's a reason why I said that, right? Because hex is 0 through 9, A through F, which is equivalent to, in decimal, A through F, which is equivalent in decimal to 0 to 15. Agreed? Isn't that 16 possible values, 0 to 15? Well, guess what? 8 plus 4 plus 2 plus 1 is 15, isn't it? So to represent the high end of the scale, which is Foxtrot, F, I would need ones to be in all 4 of these positions. To represent the low end of the scale, which is 0, I would have all zeros in those 4 positions, which means I don't need 5 bits to represent hexadecimal numbers. I only need 4 bits to represent hexadecimal numbers. Does that make sense? All right. So again, it's something that you kind of have to get used to. I always tell people when they're preparing to take this exam, you don't get a calculator for the test, but you're allowed to write down whatever you can when you sit down in front of the testing computer before you actually start your test. And one of the things I suggest people write down is their powers of 2 scale. Write it down to probably at least 2 to the power of 13. That way, when you're having to do calculations, you're not wasting time trying to figure out what the numbers are, especially when you're looking at that counter counting down and you're a little bit concerned about running out of time for the test and so on. I don't think you guys will have that problem. I think you guys will breeze through this exam here. But all right. So anyway, what they're showing us here is kind of up to 19. It's kind of a random number to stop at. But again, if you think of 19 and you think of powers of 2, 16, 32, right? Somewhere between 16 and 32 is 19. So I know I'm going to need at least 5 bits to represent 19 because 2 to the power of 5 is 32. If I did 16, which is below 19, that would only be 4 bits. It wouldn't be enough bits to represent 19. That's why you see 5 bits listed there. This is the 2 to the power of 1. This is the 2 to the power of 2. This is the 2 to the power of 5. So that is 16 plus 2 is 17 and 18 plus 1 is 19. All right? I think you guys get the general idea. If I went above 32 and I went to 33, guess what? That means now I need an additional bit because 32 is 2 to the power of 5. 33 is above that, which means I now need to go to 2 to the power of 6, which is 64. So always in your head, when you're dealing with binary, you're always thinking in powers of 2. 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, etc., etc. All right? Something to definitely keep in mind. So they do give us the table here, the binary to decimal conversion table, this powers of 2 table. And again, it's all about the position of the bit. 2 to the power of 7 is 128. If that bit is turned on, I'm going to add 128 to my overall decimal weight. 2 to the power of 5 is 32, so I'm going to add 32, which is 160. 2 to the power of 4 is on, so that's going to be another 16, so that's 176. And then we add 2 to the power of 3, which is 8, and also the 9. So that gives us a total of 185. And of course, you could do this the other direction as well. You could be given a whole binary string, and then based on that binary string, you can convert it to decimal, right? Or vice versa, decimal to binary, where you're basically just subtracting instead of adding. So if I had 185 and I said convert that to binary, I would say, okay, 185 is less than 256. So I don't need the 256 bit. But it's greater than 128. So I'm going to subtract 128 from 185, and then I'm going to keep doing that until I get to the final iteration, which gets me my final number. Hopefully that makes sense. The other direction, like I said, we just talked about that, decimal to binary. It's the same concept. In this case, 147. So again, I'm going to say, okay, 147 is higher than 128, but less than 256. So I'm going to turn on the 7th bit, actually technically the 8th bit, because we always start at 0. I'm going to turn on the 8th bit. I'm going to subtract 128 from 147, and that's going to tell me that, hey, I need whatever value. Okay, so if I said, for example, 147 minus 128, 147, try that again, 147 minus 128, so we're talking about 19. So in that case, I'm saying, okay, it's less than 32, but it's more than 16. So I'm going to go ahead and add the 16, and then I'm left with 3, and then I can add the 2 and the 1 and get to finally my final position. All right. Again, I keep saying this, but it doesn't really matter what the size of the decimal number is. It doesn't really matter what the size of the binary string is. If I gave you a number of 100,000 and I said convert that to binary, I'm going to say, okay, well, 2 to the power of 16 is 65,000. 2 to the power of 17 is 128,000 something. So I know I'm going to have at least the 16-bit turned on. So I'm going to take 100,000 minus 65,536, and then I'll continue to reduce it from there. All right? So what is the process? The process is pretty straightforward. Number 1, make a table with your powers of 2 values, what we call the radix scale. And we're going to make that table as large as we need or as small as we need, depending on the type of number that we're going to represent. Look at the columns. What is the greatest power of 2 that is less than the value? That is basically what I was just describing, right? 128 is less than 147, so I'm going to put a 1 in that column. I'm going to subtract 128, and the result is 19. Now I'm going to look for the greatest power of 2 that's less than 19, and I'll keep doing that until I reduce it all the way down to 0. All right? And then that becomes my binary string. It becomes muscle memory after a while, by the way. It's not something that you get used to just doing it, and then you just do it. It's just, okay, well, it becomes kind of second nature after you've done it for a while. All right? I'm not going to go through all of those 11 bullet points. I think you guys get the idea of what I'm trying to describe here with regard to how to do that conversion. All right? And again, the hex conversions, even though the book doesn't really discuss it, if I was to go back to, say, for example, our example, which in this case was 181, do you guys remember how we converted that to hex? We take the binary string, right, and we put that binary string together. Let me get rid of all the spaces here. And from the right to the left, we put those values into what we call nibbles, which are 4 bits each. And then we simply convert those values, those individual nibbles, to their equivalent hexadecimal value. So 1011 is 11, which is Bravo, right? In the decimal to hex conversion scale, A is 10, B is 11. And then the next number here is 5, which happens to be 5 in decimal, which is 5 in hex. So 181 is equal to 0x Bravo 5. All right. We always put the 0x, or at least some indication in front or after the number. Sometimes you might see it written as Bravo 5H with a little h. But there has to be something that indicates that it's hex, right? Because if it doesn't have alphabetical characters and it only has numbers, how do you know that you're not trying to represent some sort of decimal number as opposed to a hexadecimal number? So, all right. Another important concept, of course, is how do we represent addresses? This concept applies to both IPv4 and IPv6. Every single address, what we would refer to as a prefix, every single prefix has a corresponding subnet mask. And the purpose of the subnet mask is to define the scope of the network, all right? This room, for example, that we're in here, you see the divider in the back of the room. If I wanted to make this room bigger, I would open up that wall and I could fit more people in the room. That's an example of creating a supernet. By closing that wall right there, I'm creating 3 separate rooms, 3 different broadcast domains. That is an example of subnetting. The way that we can control that, the way we can control the size and the scope of a network is with the subnet mask, okay? So that is the purpose of a subnet mask, is to define how large the broadcast domain is, period. That's the only reason for having the mask. All right? The more ones you have in the mask, in other words, the more of the dark blue that you have and the less of the light blue that you have, the bigger the room. All right? Well, actually I should say the opposite of that. The smaller the room. Because these bits here represent the number of networks. They don't represent the size of the networks. The aqua color here, the light blue color, represents the size of the network. So if this side is larger, then you have more hosts, but you have fewer networks. If this side is larger, you have more networks, but you have fewer hosts. And that's really what the concept of subnetting is. That's what the concept of supernetting is this idea that you're adjusting the boundary of the mask to change the size of the network. And it works exactly the same way in v6 that it does in v4. A /64 prefix length in IPv6 gives me an equal number of subnets and an equal number of hosts per subnet. If I change that to a /80, I get more networks, but I get smaller networks. They're still pretty large, but you get the idea. So when we go, we're going to do that later today, when we go through this section here and we start to do our subnetting, we're going to talk about making the mask larger or making the mask smaller. Making the mask smaller is subnetting. That's basically what subnetting is. Making the mask larger is called supernetting, but we also might use it for something called summarization, where we're taking a bunch of routes and we're summarizing them as a larger route or a larger prefix. All right? It's really important that the IP address alone is not the most important piece. The subnet mask makes a huge difference. If I gave you this address, for example, 10.61, and I gave you another address, 192.168.10.65, and I said, are those clients in the same subnet? You wouldn't be able to answer that question, because you can't answer that question until you know what their mask is. You could assume the mask based on the class. You could say, oh, that's a class C, so that's /24. So yeah, those guys would be in the same subnet, but we don't know that. We don't have to use a classful mask. So you say, okay, well, let's make it a /24. Sure enough, let's put these guys with a mask of /24 and put this guy with a mask of /24. Yes, they're in the same subnet. If I change it to a 25, they're in the same subnet. But if I change it to a 26, they're not in the same subnet anymore. The first host is in subnet 0 and the second host is in subnet 64. So just by adjusting the mask slightly, by 1 bit, you can change completely how these clients communicate with each other. 65 and 61 with those subnet masks would not be able to talk to each other unless they went through a router. So 65 is not going to ARP 61. 65 is going to try and ARP its gateway to get to 61 because it knows mathematically I'm not in the same subnet. If you did something like this, now 65 thinks it can talk to 61 without a gateway because 65 thinks it's in the same subnet, but 61 doesn't. See what I'm saying? 61 says, oh, my network is from 0 to 63, and the next network is 64, so 65 is outside of my scope, outside of my broadcast domain, so I'm going to have to use a gateway to talk to that client. So I always teach my students that the subnet mask plays probably more of an important role in defining how clients communicate and how routing works and how communication works than the actual destination prefix or destination address itself. So it's very important that you understand that relationship. And again, it doesn't matter if it's V4 or V6. Ultimately, when it comes down to V4 and V6, how are the addresses represented? Ultimately, binary, powers of 2, right? So all the math that we're going to learn about subnetting this morning, understanding how a subnet works and so on, the math is applied the same way with IPv4 and IPv6. All right, now in IPv4, there is a hierarchical concept. The networks themselves, the subnetworks themselves, have 2 specifically reserved addresses. One's called the network ID, the network portion of the address, and that is represented by the 1s in the subnet mask. All right, now when I say that, it's represented by the 1s in the subnet mask. Let's take this one as an example. 192.168.10.65/25. By the way, this is often mistakenly referred to as CIDR notation. I wouldn't say it's mistakenly referred to as CIDR notation, but because this is classless, but it's what we define as the prefix length, meaning the network ID length. And it basically just means the number of 1s in the mask. So in this mask, there's 25 1s. In this mask, there's 26 1s. If you have a /10, 10 1s in the mask. If you have a /19, 19 1s in the mask, and so on. There's a little table that I always show people. It looks a little bit like this. Maybe something that would be useful for the test. 2nd, 3rd, 4th. And let's start with /8, /9, /10, /11, /12, /13, /14, /15, 15, sorry, and /16, all right? And in the 3rd octet, /16, /17, /18, /19, /20, /21, /22, /23, /24, and then in the 4th octet, /24, /25, /26, /27, 28, 29, 30, 31, and finally 32. So this is 0, 1, 2, 3, 4, 5, 6, 7, and 8. So that's the number of 1s. And then this is 0, 128, 192, 224, 240, 248, 252, 254, and finally 255. So the way that you read this, because one of the things that you guys are probably going to have to get pretty proficient in is being able to go from prefix notation, / notation, to dotted decimal notation with an IPv4 mask. If I said that the mask is 255.128, right, which is a /25, /25 is a 128 in the 4th octet. See what I'm saying? /19 is a 224 in the 3rd octet. /13 is a 248 in the 2nd octet. So it's kind of a quick way of doing that conversion. Eventually you kind of get to the point where you're like, I recognize all these numbers because these are the only possible values you can have in a subnet mask, because the subnet mask has to be consecutive 1s followed by consecutive 0s. But if I said 255.224.0.0, you'd say, okay, the 224 is in the second octet, so that's a /11. What does that actually mean, it's a /11? There's 8 ones there, right? Plus 3 additional ones there. That's 11 ones. So that's something that you really want to kind of get used to. It's really easy to recreate if you just write second, third, and fourth, and 8, 16, and 24, and just count up. Count up 8 bits. So 8, 9, 10, 11, 12, all the way up to 16, 16 all the way up to 24, 24 all the way up to 32. Some people say, well, wait, why is 16 there twice? Well, a /16 is a 255 in the second octet, but it's a 0 in the third. A /24 is a 0 in the fourth, but it's a 255 in the third. All right, so there's a little bit of overlap. You could do the first octet as well, start at 0 and go up to 8, but we don't really do anything in the first octet usually. Okay? So again, the network ID. Network ID is pretty critical because the network ID allows us to identify what network the client belongs to. And there's really only one place, well, I wouldn't say one place, there's a lot of places that the network ID is referenced. But certainly in the routing table, routers route to networks, they don't route to individual hosts. So we recognize the existence of networks based on their network ID. But the address itself is broken up into a network portion and a host portion. Even with IPv6, if I said it's a /80 mask, that means 80 ones in the mask. If I say it's a /95, that's 95 ones in the mask. And always, the ones represent the network portion, and the zeros, we're talking about binary values here, represent the host portion. Very important concept. If you look at a subnet mask, the ones in the mask always represent the network, the zeros in the mask always represent the hosts. Okay, and that applies to both IPv4 and IPv6. All right, so they give us an example here of an address 192.168.4.6. They're doing the conversion, if you will. So 192 is 128 plus 64. 168 is 128 plus 32 plus 8. 4 is just 4. And 6 is 4 plus 2. Just a different way of kind of representing that. Okay? So the next task that we're going to do is actually a really, really useful example and quite practically very, very important. So let's kind of break this down. Let me open up Wireshark so I can kind of cross-reference an actual packet capture to what we're seeing here on the slide. Because we did break down yesterday, right, the data link layer header, the Ethernet 2 header, right? What did the Ethernet 2 header break down into? 3 different fields: destination MAC, source MAC, and type field. This is what an IPv4 header looks like. And it looks a little bit confusing because we see quite a few fields. I don't need to keep capturing here. I just want to grab an individual datagram so that we can kind of cross-reference it to what we're seeing in the actual header. So let's break this down. The first thing we see here is the version field. Very simple. It's a 4-bit field, 4 bits long, a nibble, right? 4 bits long to represent the version of IP that you're running. And if I go back and I look at my Wireshark capture here, and I expand my v4 header, sure enough, the first 4 bits represent the version. A 0100 represents version 4. A 0110 would represent version 6. Right? Because 4 plus 2 is 6. So that's a very, very simple field. Is this an IPv4 header or is this an IPv6 header? Guess what you Take a guess what the very first field is in an IPv6 header. Version. And it's 6, right? So this is, and if you think about that, it makes sense, right? If a router's trying to process a packet, it knows it's already going to be, well, we would know from the type field in the data link layer header anyway, but it knows that it's IP, but it needs to be processed by IPv4 or IPv6, so the version field allows us to identify that. The next field that you see, let me go back to the slide here, is something called IHL, or what we call IP header length. That's also a 4-bit field. All right, and it describes the size of the header, not the payload, but just the header itself. Whenever you see any header that has a header length field, that tells you that that header can change in size. Sometimes it might be 20 bytes, sometimes it might be 32 bytes. It just depends. IPv6 doesn't have a variable length header. IPv6 headers are fixed in length. They're 40 bytes. So there is no header length field in an IPv6 header. But sure enough, if I go to the Wireshark capture, I can see here that the header length is identified as 20 bytes. The actual decimal value is 5, but there's a calculation that's done that says, hey, if this is 5, then that means it's a 20-byte header. Okay? The next field that we see is a rather complicated field overall. It's a simple process. I mean, it's a simple field in it's what it's used for and what its purpose is, but it's a pretty complicated discussion. It's called the toss byte. They mentioned it as the service type, but really it's called the toss byte, the type of service byte. And I'll give you kind of a quick crash course in the toss byte. This is a marking field for QoS. That's the point of this field. It's to stamp the packet with a number. And then I can create a policy on my routers that say, hey, if you see a packet with this number, do this. Right? It's for quality of service. Remember we talked about that yesterday or day before. We said quality of service is a lot of things, but classification and marking is one of those things. Now, originally, it was it's always been an 8-bit field, but it was a 3-bit value. All right? So that means that 5 of those bits were just not used, and only 3 bits were used. And it was the top 3 bits. It was the most significant bit, and then the second and the third. So you had 3 bits to mark packets, which means you had 0 through 7 possible markings. All right? And that's what most people simply refer to as type of service. Type of service, TOS. That's why it was called the TOS byte, because it was type of service. All right? But over time, and in the old days, 8 different classes of traffic was fine. You know, we had some data traffic, we might have had some mission critical traffic, but we didn't have all the types of traffic that we have today. They changed from using classic QoS, where we use this 3-bit toss field, to something called diffserv, which stands for differentiated services. All right? So instead of using 3 bits in that field, we went from a 3-bit marking to, in essence, we'll call it a 5-bit marking. It's actually a 6-bit value, but it ends up being 5 bits based on how it's used. And this is called a DSCP value, not the toss byte, not the toss value, but a DSCP value, differentiated services code point. Okay? Bottom line, it's still just marking. It's still just marking. Let me pull up a diagram. All right? So here's the table that I was going to show you guys. It looks really confusing, but it actually breaks down to kind of a logical concept. If you look at the top right, you see where it says toss. TOS, type of service. That represents the whole 8-bit field. IP precedence, which was the original 3-bit classification that I talked about, only used the 8th bit, the 7th bit, and the 6th bit. So you had 0 through 7 possible markings. When they went to DSCP, the differentiated services code point, it went from a 3-bit field to a 6-bit field, which exponentially gives me many, many more possible markings for traffic. All right, now I said it was a 5-bit value. That's because the first bit, if you look, these are the 8 bits here. So bit 1, bit 2, bit 3, bit 4, bit 5, bit 6. If you look at the third bit, it's always 0. So only the first 5 bits are actually modified to change the marking. The last bit in the 6-bit DSCP field is always 0. And DSCP breaks down, and this is kind of where it gets a little bit too complicated to go into it, but it breaks down to 2 separate pieces, class selector and discard discriminator or drop discriminator. The class selector is the first 3 bits, and then the 5th and the 4th bit are the drop discriminator. But you can see the markings here, right? So for example, voice is going to have a class descriptor of EF. That stands for expedited forwarding, all right? It's going to have an IP precedence value of 5, which is the first 3 bits, but the actual marking in the field is 10111. So again, we don't have to get into, these last 2 bits are used for things like weighted red to do, drop, to define the drop probability of the packet based on those markings, but we're not going to get into that. But you have essentially just all these different classifications now. That's really the whole point, right? That's the takeaway from this discussion. I'm sure when you do the self-study QoS piece, you might see this again. Maybe they'll go into a little bit more detail on that. But the bottom line, and this is really the takeaway from this whole discussion, is the bottom line is that field is used to mark a packet for QoS. Is this particular packet marked? Based on the Wireshark capture, it's not, right? The DSCP code point value is 0, which means that this packet has not been marked for quality of service, okay? All right, the next field, much simpler. I promise the fields get a little bit easier to understand. The next field is really much simpler. It represents the total length of the PDU. Not only just the header, because we already saw the header length before, but the total length includes the header and the payload. So I can look at this Wireshark capture and I see a total length of 268. I know for a fact there are 248 bytes of payload in this datagram because the total length field includes the header. And I've already defined that the header is 20 bytes. So 268 minus 20 is 248, so there's 248 bytes of data. All right, you could see where that might be potentially useful for you. The next 3 fields are related to each other: identification, flag, and fragment offset. Identification, flag, and fragment offset. By the way, you notice they have 2 colors here, right? They got some fields that are orange and some fields that are blue. Actually, this field should be orange as well. That actually should be orange. All these blue fields, well, now that I'm thinking about it, the protocol field is there as well. I was going to say all these blue fields don't exist in IPv6. But the ones that don't exist are header length. These 3 fields don't exist in IPv6. The checksum doesn't exist in IPv6, and options and padding don't exist in IPv6. Version does. Total length is named to payload length, and protocol is named to next header, but I thought that was their intention here. I don't know why they have these color codes now that I'm thinking about it. As I say it, I'm thinking, well, it does kind of, but it doesn't really. All right. Anyway, these 3 fields are all related to each other. All right, these three fields are related to something called, related to packet fragmentation. This is something that I kind of alluded to yesterday, and I'm glad that we're discussing it today because I think it's really important to understand. There are two values that are used in the transport of data that allow us to identify how much data can be carried inside of a PDU. There's something called an MSS, and there's something called an MTU. MSS stands for maximum segment size. MTU stands for maximum transmission unit length. MSS is layer 4, MTU is layer 3. So if this PC, and we'll see this when we get into our TCP discussion later on, this PC wants to establish a TCP session with this PC. They're going to do their three-way handshake. They're going to establish their TCP connection. And in that process, in fact, let me show you in Wireshark real quick. I just have to find a three-way handshake. So that's a UDP. Let me find a TCP. And specifically, let me see if I can find a three-way handshake. Do I see a SYNAC ACAC? SYNAC ACAC? Nope. Let me try stream index number 2. That's a fan. There we go. SYNAC ACK. And this is something we're going to talk about later, but one other thing, I just want to point this out. This is the TCP header. Inside that TCP header, they're negotiating the maximum segment size. That's part of the negotiation of that initial three-way handshake. This is a layer 4 concept, not a layer 3 concept. So the clients are basically saying, when we send data to each other, let's not put more than 1,460 bytes into a TCP segment. All right, so they're saying even if you have to send me 1,000,000 bytes of information, you have to divide it up into 1,460 bytes. That's negotiated at layer 4. So let's say, for example, these guys negotiated 1,460 bytes as their maximum segment size. And so they're sending their data, and that data is going across multiple routers. But for some reason, the MTU of this link is maybe 1,200 bytes. That poses a bit of a problem because the MTU is a layer 3 construct that says you can only put 1,200 bytes into a packet. But the clients are generating 1,460 byte segments. So what has to happen is when this datagram reaches that router, it has to be fragmented. It has to be divided up into smaller pieces so we can meet that requirement. And then on the other side, the fragments get put back together and we send it on its way. So these three fields are used to manage that process. Identification, flag, and fragment offset.
Are those fragments usually about the same size?
They would be, yeah, typically. We're going to fragment to whatever the maximum available size is. So we don't divide it equally across. We're going to try and create as few fragments as possible. Yeah, so we have a big one and maybe a little one, right? But that's what these three fields are used for, and we can see, well, they're kind of related to each other at least. In this case, we have an identification. We notice here there is no fragment offset, which means that there wasn't fragmentation. Fragmentation didn't occur. Also, whoever generated this datagram set the do not fragment bit. This bit is reserved for whatever, who knows. This bit is to indicate that there are more fragments that are part of this flow. This bit says you're not allowed to fragment. So if for some reason this segment or this PDU did need to be fragmented, the router would be instructed not to, and the router would simply drop it. Remember we were doing that yesterday, we were messing with that DF bit? That's the DF bit. That's the do not fragment bit. And this is established by whoever generated the traffic. I don't know what the rules are, you know, the regulations are for how we decide whether or not that bit gets set or not. I don't know how the application decides that, but we know what that bit means. That means you're not allowed to divide this data up into smaller pieces. So guess what? If it's too large, you need to drop the packet. All right? And then we will just rely on other mechanisms to retransmit or whatever. So that's what those 3 bits are used for. In IPv6, are those 3 fields, excuse me. In IPv6, these fields are not, they're non-existent because fragmentation, I don't want to say fragmentation can't necessarily occur in IPv6, but there's a process in IPv6 called Mtu Path Discovery, where the clients will identify how large what the minimum MTU is along the path before it actually builds the PDUs. The next field we have is our time to live field. Very, very important field inside of IPv4. We can see based on highlighting that particular field, let me go back to it, time to live. We can see that that is an 8-bit field, right? 2 hexadecimal characters. Yeah, there we go. 2 hexadecimal characters means that that's an 8-bit field right there. Right there, sorry, 80. All right. Now, time to live defines the life of the packet. If you're routing packets through the network, let's say here the TTL was set to 10. And it's the originating host that defines what that time to live is. Every time you route that packet through a router, not to a router, but through a router, that value gets decremented by 1. All right? Very, very simple concept. When that value reaches 0, guess what? The packet gets dropped. So it's a way to prevent packets from looping indefinitely if they get stuck in a routing loop or something on the internet or in your enterprise or whatever. It's a very, very simple field. It was called time to live because originally it was defined as a timestamp. Originally there was a timestamp. But the problem with the idea of applying a timestamp is that everybody's clocks had to be synchronized, and that wasn't very reasonable for the internet, right? So we don't do that in this particular case. All right. So in our case, the time to live was set to 128. That's a pretty typical Windows setting. Windows typically will set the time to live to 128. But it depends on the vendor. Cisco likes to use 255. Interestingly enough, if I was to look at, say, like multicast traffic, say, for example, 224 multicast traffic, the time to live for those packets is set to 1 by default. That allows us to limit the scope of that multicast traffic. The protocol field is also a very, very simple field. It is a 16-bit field. We can see that, or excuse me, an 8-bit field. We can see that here, 06 in this case. But the protocol field allows me to identify what protocol is next. We can see in this particular case, in our example, the protocol field is 6, which is TCP. Remember we looked up those protocol numbers before? Protocol 88 is EIGRP, protocol 89 is OSPF, protocol 1 is ICMP, protocol 17 is UDP, and so on. So protocol field, very, very simple. It's just a way for us to identify what is being encapsulated inside of IP. Checksum, also a very simple field. If we look at the Wireshark, that checksum value is, let's go down to checksum, is a 16-bit field. We can see that here, E481, so that's a 16-bit field. Checksum is to IP like the frame check sequence is to the data link layer. We do a hash calculation, we do a mathematical calculation, we put the number into that field, and along the path, everybody that's processing this packet verifies the integrity of the data by verifying that that checksum matches. All right? It does take a little bit of time. IPv6 got rid of that field. There is no checksum in IPv6, but it is in IPv4. And then last but not least, the last two fields, source and destination address. 32-bit fields, source IP, destination IP. Okay? Hopefully that at least gives you an idea now of the packet header. And we talked about this kind of in the beginning when we were talking about the overall encapsulation process. There's only one field in this entire header that is fundamentally used to make a routing decision. Destination IP, right? But you could see where the other fields will influence how the router routes as well. For example, time to live. If the act of me routing the packet means that the time to live goes to 0, then I'm not going to route the packet. If this is a fragment, then I have to treat the packet slightly differently because it's a fragment. If there's a DSCP value applied to this field, then I'm going to go ahead and process this packet based on that marking. But ultimately, when it comes down to it, routing is all about this field right here. Unless it's multicast, then routing is about this field, believe it or not. Multicast routing is the reverse of unicast routing. All right. Next thing we'll talk about is the V4 classes. Back in the day when Al Gore was coming up with the whole concept of the internet, he decided that there weren't going to be that many people on the network, right? Obviously that was a joke, but you get the idea. That reference is kind of getting old. I probably should stop saying it because a lot of people might not know what I'm talking about. But anyway. Everybody knows Al Gore invented the internet, yeah. But these classes that they defined, what they basically said is they said essentially, look, and there's a reason why this happened, by the way, and I'll describe that in a minute. But they said basically, look, let's go ahead and predefine the subnet sizes, the network sizes based on the class of the address. In other words, if you had an address in the class A space, you always had to have a /8 mask. You always had to have a 255.0.0.0 mask. If you fell within the class B space, you always had to have a /16 mask. And if you fell within the class C space, you always had to have a /24 mask. There's a reason why this occurred. All right? Prior to, and I don't know if I can find it. Let me see if I can find it real quick. So I did find it here. So prior to, we'll say 1990, right? Prior to 1990, the protocols themselves, the routing protocols that were invented, did not send subnet mask information along with the routing updates. They just sent IP information. So we always had to assume what the mask was, and it was based on those classes, Class A, Class B, Class C, Class D, and Class E. This is what we refer to as classful routing. Classful routing means it's a bad thing. It means the routing protocols didn't understand subnet masking. In the 90s, they got away from that. There was actually an RFC for classless interdomain routing, RFC 1519, that got away from the strategy of only advertising prefixes, and they said, you know what, let's rewrite the routing protocols so that they will send subnet mask information along with the routing information so we don't have to be bound by these classes anymore. So this is really the RFC that really kind of changed how we do networking today, because they realized very quickly they were running out of network space. They were running out of address space. I mean, think about it. You had universities and organizations getting assigned a Class A address, but they could not divide it up. They could take that Class A address and they could assign it to a network. How many clients exist in a Class A address? 2 to the power of 24 addresses minus 2, of course. So you would have 16.7 million hosts in one broadcast domain. That would be equivalent to saying sticking 16.7 million people in this room. And that's the only way in and out, that door. Obviously, you didn't have networks that size. But so they would get a Class A address and they would assign it to a network that might have 500 hosts, and the other 16.7 million addresses just would not be used, could not be used. So when this RFC was released, it talked about, it was released in 1993. Actually, the original RFC was 1338, which was released in 1992. Supernetting and address assignment and aggregation strategy, similar. But basically this RFC, this 1519 RFC, identifies how we can change how interdomain routing protocols work by sending subnet mask information along with routing information. Which means now subnetting can exist, variable length subnet masks can exist, and so on. So right around this time, 1990, 91, 92, this is the heyday of routing. This is where routing protocols really became mainstream, right? OSPF and EIGRP. Notice the very first routing protocol, IGRP. EGP was a routing protocol, but it was used for external routing, like on the internet. IGRP was the very first interior routing protocol, something you would use in your enterprise, that was developed by Cisco in 1985. And then 90, 91, 92, all these protocols came out. And guess what? All of those protocols are classless, which means they support subnet masking. All right, they support subnetting, excuse me, because they send the subnet mask information along with the routing updates. So we still talk about the classes as if they somehow exist today. They don't really exist, but we still need to know where we're coming from, right? We need to know how the subnet mask was originally defined. But the reality is classes don't really matter anymore, okay? IPv6 was never classful. IPv6 has been around for a long time. It was actually became a standard in 1996. It was developed before 1996, but IPv6 was actually a standard in 1996, but that was clearly after that 1993 RFC. All right? So the Class A space provided you a very few number of networks, but it gave you really, really large networks. Class B was kind of a mix, right? Half and half. 16 bits for networks, 16 bits for hosts, and then Class C, only 8 bits for hosts and 24 bits for networks. All right? Now, mathematically, let me see if they actually have that here. Yep, they do. By the way, Class D, wasn't listed in that diagram, but Class D has a special use case in IPv4. Class D is multicast. Every address in that range is a multicast address, and Class E, to this day, is reserved for special use. Experimental class. I don't know who's experimenting with it. I've never seen anybody actually use it. Yeah, I've never seen an example myself, you know, of somebody using this experimental class. But I don't even think you could really use this on like a modern operating system. If you tried to assign an address in that space, it would just say, no, you can't do that. So I'm not sure what kind of experiments people are doing to use that space, but all right. So mathematically, how does it break down? Even though we don't really care anymore, you still need to know it for the test. Class A is 1 to 120, actually, technically, mathematically, 0 to 127. 127 is missing from here because it's used for one single purpose, which was a little bit not very well thought out either. I can ping any 127 address, 45, 45, 95, and if I get a reply, that tells me that my protocol stack is working. It's a way for me to test the IP stack software on my computer. So they took 16.7 million addresses to do the same thing. At least in IPv6, they only created one loopback address, and that was :1. That's the only loopback address for testing the protocol stack in IPv6. But so 127 is still considered Class A. It falls mathematically within the Class A range. If you look back at this chart here, you can see what they did to define the classes. They said, let's fix the first bit at 0. Let's fix the first 2 bits at 10. Let's fix the first 3 bits at 110. Guess what Class D is? 1110. And guess what Class E is? 1111. So by definition, that's how we come up with the mathematical boundaries, right? Because this bit is fixed at 0, that includes 0 to 127. Because these 2 bits are fixed at 10, that includes 128 to 191. And because these first 3 bits are fixed at 110, that's 192 to 223, and so on. All right? There are some reserved address spaces within these blocks as well, right? The 190, now I can't think of it. PIPA 169.254 range. The 169.254/16 range is reserved, but it still falls within the Class B space. And then we have our RFC 1918 address space as well, which is our private addressing. So Class D is multicast 1110. Class E is reserved 1111. All the underlined pieces are the fixed bits, and so on. All right? All right. So the subnet mask. I've already mentioned this a couple of times. The subnet mask is really a way for us to define the makeup of a network. Again, the ones portion of the subnet mask corresponds to the network portion of the address. The zeros portion of the subnet mask corresponds to the host portion. But here is the golden rule for a subnet mask. It always has to be consecutive ones followed by consecutive zeros. You will never see a subnet mask that has a mix of ones and zeros, meaning 111, 011, 011, 1100, because again, the ones do represent something specific. The first 24 bits of this address is, the first 16 bits of this address is the network. The last 16 bits of the address is the host range. By the way, that works the exact same way in IPv6. If I give you a /64 mask in IPv6, the first 64 bits represent the network, the last 64 bits represent the host. If I give you a /50 mask in IPv6, the first 50 bits represent the network, the last 128 minus 50 bits represent the host. Does that make sense? All right. We'll see more about that a little bit later on. So the next thing we're going to talk about is calculating the network ID. All right. They go through an example here. The mask is a way for us to kind of to identify the network and the host. And what they're doing is they're doing a Boolean AND operation. Let's talk about that because there's 2 primary Boolean operations that you're going to see in networking. There's an AND operation and there's an OR operation. All right? You guys, by the way, happen to know where this comes from, right? This whole concept of Boolean math, how computers basically work, right? What is the one primary component of any computing system? Tiny little piece of electronics. Well, yes, the CPU, but what is the CPU made of? Transistors, right? This is what a computer is made of, transistors. The logic gates, 3 pins, right? 2 inputs, 1 output. Pretty straightforward, right? And if you look at like an 88 CPU, 8080 or 8080 CPU number of transistors, and you look at, let me see, it had 6,000 transistors. And if you look at an i10 processor, transistors. That's where we're getting all the computing power from now. How many transistors are in these processors? It's in the millions, right? Or billions. 1.4 billion transistors in an i3, 1.7 billion in an i7 processor. So it's an interesting concept. There was a Wikipedia page that, right here, transistor count, that listed all the transistors, and there's some pretty powerful ones. You get down to this down here, you got 5.5 billion in that 18-core Xeon processor, 8 billion in this 28-core Pentium 8180, 30 billion in this Graviton 2. That's a really expensive CPU. But here's the idea. Amazon developed that. That's kind of interesting. Designer by Amazon. It's a pretty powerful CPU, right? Probably for their, well, this one's even more powerful, almost 40 billion transistors, AMD. Yeah. But the idea is that we're able to push more parallel operations through the CPU because we have so many transistors to process this. So it's very interesting. It goes back to my electronics days, but it's very interesting that that is really the core component to any computing system, because that's what we talk about here. When we're talking about doing these calculations, it basically boils down to Boolean operations. An AND operation is if it's a 0 and a 0 input, the output is a 1. If it's a 0 and a 1, the output is a 0. If it's a 1 and a 0, the output is a 0. And if it's a 1 and a 1, the output is a 1. So AND literally means if both numbers are the same, the result is a 1. All right? Not sure why the book says 0 and 0 is 0. 0 and 0 should be a 1. Let me just confirm that. All right, so I corrected that. In the OR operation, like I said, if one or the other number is a 1, then the output is a 1. So the OR operation would be 0 and 0 would be a 0. A 1 and a, let me do it the same way. A 0 and a 1 would be a 1. 1 and a 0 would be a 1, and a 1 and a 1 would be a 1. All right? So that one's pretty straightforward. And the reason why I bring this up is because the way that you can calculate these values, the way that you can calculate, say, a network ID and a broadcast ID is to do these Boolean operations. I'm going to show you an easier way to do it where you don't have to worry about the Boolean operations, but they're saying the result of the AND operation ends up being the network address of the network on which the device resides. So if I take the IP address in binary format and I take the subnet mask in binary format, the end result is the end result of the AND operation is the network ID. All right? It's quite simple, though, just to simply say, look, if it's a 1, it represents the network. The address starts with 172.16. The first 16 bits are 1, so the network ID is 172.16. Makes sense, right? It gets a little bit more complicated when you start to get into where you're not falling in major classical boundaries. This is falling in a major classical boundary, but let's say it wasn't a /16. Let's say it was a /17. That means that this bit here would also be a 1. All right? Well, a 0 and a 1 would be a 0. And that represents the network is still going to be, well, it's going to start with 0 in that particular case. All right? And then they did another example here. I'm going to show you guys how to do some subnetting calculations in a little bit. Probably after our break. We're getting close to the break time. And we're going to go through some examples together, and I'll show you guys how to do some of those calculations. So what is a subnet? Why would I want to create subnets? Why would I want to take a big network and divide it into smaller pieces? Well, there's a concept in networking called a broadcast domain, right? And the scope of a broadcast domain is if I send a broadcast packet, how many people have to process that datagram, right? This room is a broadcast domain. Now think about it if this room had 100 people in it, or this room had 1,000 people in it, and everybody was talking at the same time. We would call those broadcast messages, right? The room would get very noisy, and probably we would get overwhelmed with the amount of traffic or the amount of noise that's being generated in the room. So if I took these rooms and divided them up into 3 smaller rooms, and I divided the people equally among those rooms, then the broadcasting that occurs in this room doesn't affect the other users in the other room. And that's basically what a subnet is. A subnet is a way for us to logically separate a large broadcast domain into smaller broadcast domains, so that if somebody is sending a broadcast in one network, it doesn't affect the other users in other networks. What device in our topology prevents those broadcasts from being propagated? A router. Routers never ever forward broadcasts, ever. They can create them, they can generate them, but they never forward them. So if I am on subnet A and I send a broadcast, when it gets to that router, that broadcast stops at that router. Routers by design never forward broadcasts. So every interface on a router is a separate broadcast domain. Every interface on a router is a separate broadcast domain. Now there may be other reasons that you decide to divide the network up into smaller pieces. Certainly security would be something that we would consider, right? Because by segmenting the network into different VLANs or different subnets, I can now apply security policies between those zones to say this traffic is allowed or this traffic is not allowed between those networks. It's going to make it easier to isolate problems. It allows us to, address space resolution is an interesting concept because subnetting actually reduces the number of addresses that you have available to you. If I had one large network, I only have 2 addresses that are reserved for that one large network, the network ID and the broadcast ID. But if I take that one large network and I divide it up into 20 networks, then all of a sudden I have 20 network IDs and 20 broadcast IDs. So I'm actually reducing the number of usable address space, but I'm making the network more efficient. And that's really the benefit, the scalability and speed. In this particular topology, everybody's in the same broadcast domain. So if this PC here on the left sends a broadcast, that's going to get flooded throughout the network, and everybody's going to have to process that datagram. Whether they end up using it or not is a different story, but they do need to process it. All right? And that's where subnetting comes into play. So if I put a router in between, this client over here can send a broadcast, but that broadcast will only reach, well, not even that client, will only reach those 3 clients. Because we have 4 separate broadcast domains now in our topology. If I have a router with 4 interfaces, I have 4 broadcast domains, period. All right, so broadcasts in this network do not affect the clients in this network or the clients in this network. And you can understand why that would provide more efficiency in our design. The calculation of this is what's important, being able to implement the subnetting, being able to do the calculations and so on. And that's what we're going to talk about after our break. All right? So the next thing we're going to talk about is subnetting. And they do talk about basically the idea of subnetting is us borrowing bits, right? Taking bits away from the network or taking bits away from the host portion of the address and basically converting zeros to ones. Making the mask longer creates more networks, but the networks become smaller. It's kind of like saying putting these dividers up in the room makes the room smaller, but it gives us more rooms. more individual rooms. And that's basically what we do with subnetting. We mathematically modify the subnet mask, or at least change the makeup of the subnet mask to what we call borrowing bits to create those subnets. So to implement subnets, follow the procedure. Determine the address of your network is assigned, the IP address for your network as assigned by the registry authority. Let me talk about that real quick, because this assumes, of course, that you're talking about publicly routable addresses, but there are 5 regional internet registries that exist globally. And that would not be the right picture. That looks like some medical stuff. Let me do this. Regional Internet Registry. All right, there we go. So there are 5 regional internet registries that exist. The global organization that is responsible for these for address assignments is the IANA, but then you have these 5 different regional internet registries. RIPE, which is for Europe, AFRINIC, which is for Africa, APNIC for Asia Pacific, ARIN for North America, and LACNIC for Latin America. And basically what happens is the IANA allocates address space to these regional internet registries, and then the regional internet registries allocate address space to the rest of the customers, the service providers. Now, if you go out and you search for these global address assignments, IANA, Ipv4 address space, you can see how these addresses were allocated. So, for example, if I sort by date, we can see that the very first block of addresses, the very first prefix was allocated on January of 1991. Actually, several. This was for DLA. This was for Asia Pacific, for ARIN, DISA, Defense Information Systems Agency, ARIN, Apple Computer, ARIN, and so on. So these are the prefixes that were allocated based on these dates, right? And if I go all the way to the end, guess when the very last public address space was allocated? 2011. So that's it, no more. As of 2011, there are no more prefixes. This one was allocated to RIPE, which is Europe, Latin America, ARIN, Asia Pacific, and so on. So when they say in the book here, they're referencing this idea of determine the address that for your network as assigned by your registry authority. That's what they're talking about. Does that mean that you can only subnet public addresses? No, it doesn't. You can subnet internal private addresses as well, and we do that all the time. So I don't know that this bullet point is really that critical, because again, you can subnet any kind of address. It doesn't matter if it's private or public. Based on your organizational and administrative structure, determine the number of subnets that are required for the network. So that is actually in Plan for Growth. That is actually the first calculation that we are going to talk about. Calculating based on the number of subnets. There's basically 3 different calculations when it comes to subnetting that you guys have to be familiar with. Calculating based on the number of subnets, calculating based on the number of hosts, and calculating the anatomy of the subnet itself. So let's start by talking about calculating based on networks, or what we call subnets. So let's say, for example, I have an organization and I was told by my boss, you were given this address, 10.10.0.0/16, okay? That's the prefix that you were given as an organization. You need to create as many subnets as possible sorry, let's not do it that way. You need to create 300 subnets with as many hosts per subnet as possible. In other words, make the subnets as large as you can, but you need at least 300 subnets. And that's what they're referencing here. In that bullet point, it says, based on your organizational and administrative structure, determine the number of subnets that you need for your network. All right? There's a formula that we use to do this calculation. That formula is 2 to the power of n equals subnets where n is equal to the number of borrowed ones. Okay? So quick question. How many ones exist in the original network? How many ones exist in the original network? 16, right? Slash 16 means 16 ones. You guys agree with that? How many ones could I borrow? Meaning how many zeros can be converted to ones in the mask? 16. There's 32 bits in a mask. Half of them are ones, the other half are 0. So I have the potential of borrowing up to 16 ones. All right? But if I do the formula, 2 to the power of n has to be greater than or equal to 300. That was part of my requirement, right? 2 to the power of n has to be greater than or equal to 300 because I need at least 300 networks. Then I just simply solve for n, don't I? What is the number that's going to meet that requirement? 2 to the power of 7 equals 128. 2 to the power of 8 equals 256. 2 to the power of 9 equals 512. So that's the winner, right? 9. You follow me so far? In other words, I can't get to 300 subnets exactly, can I? Because we're using powers of 2 math. If I did 2 to the power of 8, that's only going to give me 256 subnets. If I do 2 to the power of 9, that's 512. That's the best I can do. The 9 is the number of borrowed ones, which means slash 16 plus 9 is my new mask. Does that make sense? I started with 16. I added 9 additional ones, which is 25. So slash 25 is my new mask. This, of course, assumes that every subnet is exactly the same size. It's what we call common subnetting. We're making every single subnet the same size. I'm going to create 512 subnets by changing my mask from a slash 16 to a slash 25. We don't know what those subnets are yet. I'm going to show you guys how to do that calculation as part of this discussion as well. But I'm going from a slash 16 to a slash 25. Let's do a couple of more examples here because I want to make sure you understand this calculation. Calculating based on the number of networks. Again, the formula is 2 to the power of n equals subnets where n is borrowed ones. All right, so let's look at this from a different perspective. I started with a slash 24 and I ended with a slash 27. How many subnets did I create in this particular case? Remember the formula, 2 to the power of n equals subnets. How many bits did I borrow? I started with a 24 and I went to a 27. How many bits did I borrow? 3, right? 2 to the power of 3 equals what? 8? Yes? No? 8 subnets. All right. We don't know what the subnets are. I don't know how large they are. I don't know how many hosts there are. I just know that I created 8. I mean, I do know, I could calculate those numbers, but that's not what we're doing right now. We're basically just focusing on one calculation, which is probably not very practical in reality, because we don't usually build our networks based on the number of networks. We usually build our networks based on the number of hosts, right? How about this? I have a 2001 DB8 let's do ACAD 1 :, actually let me just do this, /48, and I need 20,000 subnets. What mask would I use? Now I know we haven't talked about IPv6 yet, but /48 in IPv6 means exactly the same thing as /17 is in IPv4. It's the number of ones in the mask. So it doesn't matter that it's an IPv6 address. The calculation is exactly the same. 2 to the power of n has to be greater than or equal to 20,000. That seems like a large number, but again, because we're dealing with powers of 2, it's not really that big of not that difficult of a calculation. 2 to the power of 7 is 128. 2 to the power of 8 is 256. 2 to the power of 9 is 512. 2 to the power of 10 is 1024. 2 to the power of 11 is 2048. 2 to the power of 12 is 4096. 2 to the power of 13 is 8192. 2 to the power of 16 is 16384. Right? You guys follow me so far? Okay. So we're talking about what? 2 to the power of 17? All right. What is 2 to the power of 17? 32,768 is what it should be, right? 2 to the power of 17. Sorry, I did my math wrong. Because 2 to the power of 16 should be 65,535, so I must have messed up something. 2 to the power of 16 is 65,535. 2 to the power of 15 is 32,768. That's what I need. 2 to the power of 15. I don't know where I messed up that calculation. So that's 32,768. So we're talking about 2 to the power of 15. I must have skipped something. It's lunchtime, so I'm not thinking correctly. But you get the idea. The point is we're still doing our powers of 2 calculation. 2 to the power of 15 equals 32,768. So what is 2 to the power of 14? 16,384. I don't know where I got 16 from. I mean, 16 is one of the easiest fields to calculate because there's so many headers that use 16-bit fields. But anyway, we've calculated at 2 to the 15, which means my new mask needs to be what? /48 plus 15 /63, right? So it's a very simple calculation. Based on the number of subnets, we use a simple formula, and we say, okay, how many bits am I going to borrow to create those subnets? All right? Now, we still need to know what those networks look like. We still need to know how those networks are, where they begin, where do they end, what's the network ID, what's the broadcast ID, and so on. You guys want to do a couple more? Let's do a couple more. All right. So I have 172.16.10.0 with a mask of 255.255. Let's do with a 10, I would have to do like a 252.0. All right. And I need 155 subnets. 2 to the power of n has to be greater than or equal to 155. 2 to the power of 7 is 128. 2 to the power of 8 is 256. That's going to be our number, isn't it? 2 to the power of 8. Agreed? 2 to the power of 8 is equal to 256, which means 8 bits borrowed. But I did it a little bit differently here, right? I didn't give you the prefix notation originally. I gave you the dotted decimal notation. What is the prefix length for 255.255.252.0? You say a /22? We know it's 8 at least. There's 8 ones. There's another 8 ones, so that's 16. And this is an additional 6. 0, 128, 192, 224, 240, 248, 252. You just have to kind of get used to that. That's that scale we talked about. 0, 128, 192, 224, 240, 248, 252, 254, and 255. Those are the only possible values you would see. This is 1 bit, this is 2 bits, this is 3 bits, 4 bits, 5 bits, 6 bits, 7 bits, and 8 bits. So this is equivalent to a /22, but we have to add the 8 additional ones, right? Which means our new mask is going to be /30. That make sense? They're small networks. They're very small networks. There's only a couple of bits for hosts, which means only 4 addresses and 2 usable addresses, but it does, we can meet the requirement. What if I said, I don't want to calculate based on the number of networks, I want to calculate based on the number of hosts per subnet. So let's say I have 192.168.10.0/24, and I need as many subnets as possible with at least 30 hosts per subnet. So now I'm calculating based on the number of hosts, not based on the number of subnets. The formula in this case is 2 to the power of n minus 2 equals hosts, and n is the number of zeros in the mask. All right? So where n is the number of zeros, not borrowed zeros, the total number of zeros in the mask. All right? So again, I solve for the formula, and then I have to interpret the value of n and what it represents. So let's say, for example, we need 30 hosts, so 2 to the power of n minus 2 has to be greater than or equal to 30. 2 to the power of 4 is equal to 16. 2 to the power of 5 is equal to 32. Which meets our requirement, doesn't it? Because 32 minus 2 is equal to 30. So 2 to the power of 5 minus 2 is equal to 30. Why the minus 2? Those 2 reserved addresses in every subnet, network ID and broadcast ID, those are not usable as host addresses, so we have to subtract those from the total. But this still doesn't tell me what my mask is. How large is an IPv4 subnet mask? 32 bits. How many of those bits are zeros? Based on our calculation, 5. That is my subnet mask, isn't it? /27. If there's 32 bits in a mask and 5 of them are 0, that means the rest must be 1. So I would have to put a /27 mask to give me 30 hosts per subnet. Now, how many subnets did I get? You guys know that calculation because we just did that. How many subnets do I get from this? You say 8? Well, we're going from a 24 to a 27, which is 3 bits borrowed. That is an 8. So we have 8 subnets, 30 hosts per subnet. Does that make sense? Kind of? It takes a little bit of practice, right? It's not something you're going to get right away, especially if you're not used to doing it. But the key is to remember the formulas. All right? When we're calculating based on the number of subnets, calculating based on subnets, 2 to the power of n equals subnets, where n is the total number of borrowed ones, and calculating based on hosts, the formula is 2 to the power of n minus 2 for IPv4 equals hosts, where n is the total number of zeros in the mask. This is for IPv4. The formula is slightly different for IPv6 because you only subtract 1 for IPv6. Insert. You understand why you subtract 1? Maybe not, because we hadn't talked about it yet. There's no broadcasting in IPv6. There is no concept of broadcasting in IPv6, so there's no broadcast address. There's a network ID, no broadcasting. All right? But let's talk about something maybe perhaps a little bit more practical. Let's talk about applying this in a kind of as an application exercise to subnetting here. So let's say I've got a router here, and that router has 4 interfaces. Okay? And we have 22 hosts in that subnet. I'm using small numbers. It doesn't matter if the numbers are big or small. The math is still the same. I have 22 hosts in that network. I have 60 hosts in this subnet. I have 33 hosts in this subnet. And I have let's do 50 hosts in this subnet. Okay? And I was given the address of 192.168.10.0/24. I have to divide that network up to meet my requirement. To meet my requirement of networks and hosts. So I can do the calculation. I can come back here and say, okay, I need 4 subnets. So 192.168.10.0/24 2 to the power of n has to be greater than or equal to 4. Okay. Can I get 4 subnets? Well, solve for n, which is 2 to the power of 2, equals 4, which means I go from a /24 to a /26. So we know we can do that. We know we can meet that requirement that way. I know that I can create enough subnets. But now what about the number of hosts? Looking at this diagram, which of these 4 networks would I base my calculation off of? 60, right? As far as the number of hosts. Assuming I'm going to apply the same mask to every network, which I don't have to do, I would say, okay, let's go ahead and base the calculation on the largest network, and let's see if dividing that network up into 4 pieces is going to meet my requirement. So now I'm going to say, okay, let's do our host calculation. 2 to the power of n minus 2 has to be greater than or equal to 60, and I solve for n. 2 to the power of 6 minus 2 equals 62. 2 to the power of 6 is 64. Minus 2 is 62. All right? Now, this one meant the number of barred ones. What does this 6 represent in this case? The number of zeros. Are there 6 zeros in that mask? 26 plus 6 is 32, isn't it? So it actually works. The math works both ways. If I use a /26, guess what? I'm going to have all the networks that I need. Okay? So I know I can do it. I know I can create the subnets. I know I can, I have enough space to have enough addresses per subnet. But here's the third and final calculation. What are the networks, right? What is network 1? What is network 2? What is network 3? What is network 4? This is the part that's pretty magical. And this is the part, by the way, that really becomes the most important part of the calculation. On the test, this is what you're most likely going to see. Okay? Let me erase this part at least. There are only 5 questions that need to be answered about subnetting. 1, what is the network ID for the LAN? Or I'll just put for the network. 2, what is the broadcast ID for the network? And that would only apply to IPv4 because IPv6 doesn't do broadcasting. Number 3, what are the usable addresses in the network? What do I mean by usable addresses in the network? Which ones can I assign to clients? Which ones can I assign to hosts? Number 4, how many subnets were created? And number 5, how many hosts per subnet are created? These are really the only 5 calculations you'll ever have to calculate when it comes to subnetting. 2 of these we've already done. How many subnets and how many hosts per subnet. Those are the powers of 2 formulas that I just talked about. For this one here, number of subnets, again, it's this formula right here, 2 to the power of n is the formula here. And then here is the 2 to the power of n minus 2 is the formula here. These first 3 things are more related to what I call the anatomy of the network. The anatomy of the network. What's the network ID? What's the broadcast ID? What's the host range? So check out this calculation here. This is a pretty interesting calculation because this is a pretty common type of question that you would get on the test. I have this address, 10.45.87.33/29. Now, answer the first 3 questions about this address. ... Okay? I'm not asking, it's rhetorical, I'm not asking you to do that, but that's what what is the network ID for that client? What is the broadcast ID for that client? What are the usable addresses? And when you go back to the book, they actually go through these calculations. This whole thing about the Boolean math, the and the ors, doing the and calculation and or calculation, that's how typically most people will teach you to calculate these values. But I'm going to teach you a little bit of a different method. All right? I'm going to teach you what I think is probably the easiest way to where you guys are going to be able to just calculate these things in your head. Right? I already know that the network ID is 32, and I already know the broadcast ID is 39, and the host range is 33 through 38. I did the calculation in my head. All right? This is not a formula, it's more of a process. And we're going to do a few of these to make sure that you guys feel completely comfortable. Step number 1, convert the mask to decimal. And there's a reason why we do this, because it makes the calculation much easier. 255, 255, 255, 248 in this particular case. All right, /29, that's just something you're just going to have to get used to. But it's 29 ones. The first 255, second 255, and the third 255 is 24 ones, plus 5 more is 248. Okay? Number 2, identify which octet you are subnetted in. And in this particular case, which octet are we subnetted in? The 4th. Right? In other words, these are all ones, right? The first 3 octets are all ones, which means that must be the network portion. By definition, ones in the mask mean that's part of the network. This is the only part of the mask that has ones and zeros, so that must be where we're subnetted. Does that make sense? Number 3, calculate your block size. Some people call this the magic number. It's 256 minus the value of the mask in the octet you're subnetted in. And in this case, our block size is 8. It's always 256 because there's always 256 possible values in an octet. 0 to 255. That's 256 possible values. Number 4, write out your networks. Your network IDs, which, by the way, all addresses divisible by the block size. So my first network is 10.45.87.0. My next network is 10.45.87.8. My next network is 10.45.87.16. See what I'm saying? The block size actually tells me the size of my networks. And because the very first address is always the network ID, all I have to do is keep adding 8 each time, and I'm going to get every single network. 10.45.87.32, 10.45.87.40, 10.45.87.48, ... We're going to go through this a couple of times, so if you don't quite get it right now, that's okay. But this is, you can get to a place where you can use this method to do all these calculations in your head. Now remember what I said originally. I said let's answer the first 3 questions about this client. Based on this being the list of our subnets, which network do you think 33 belongs to? 32. So that is the network ID for my client. If this is the next network, this is the next network ID, right? What do I know about the previous network? I know the broadcast address, because the broadcast address is always the last address in the subnet. Always. So this is the broadcast address, broadcast ID. If I know the network ID and I know the broadcast ID, then I also know the host range. because it's everything in between, which is 33 through 38. All right? This is what I refer to as the anatomy of a subnet. Now, if you've taken 10 different networking classes, you might have learned 10 different ways to calculate subnets. But again, it's really whatever you're comfortable with. If you have your own method, that's perfectly fine. There's nothing wrong with it as long as you get the right answer. Ultimately, it always boils down to binary math. We're just doing the binary math a different way. All right? So let me give you an example. I'm going to erase a lot of this stuff here. And let's say 109.76.45.113 slash, let's do a 19. Okay? Now, I know already that the network ID is 109.76.40.0. Actually, it's 32.0 in this case. 109.76.32.0. And the broadcast is 109.76.63.255. Host range is 32.1 through 63.254. I'm going to break it down based on the calculations, but I'm in my head doing the same steps that I just showed you. I'm saying, oh, a /19, that's a 224 in the third octet. 256 minus 224 is a block of 32. The closest thing to 45 divisible by 32 is 32. 32 plus 32 is 64, so 64 is the next network, which means 63 is the last address. You see what I'm saying? I'm going through those steps in my head. So let's do step number one. What is the mask in dotted decimal format? 255, 255, 224.0. Which means I'm subnetted in the third octet, which means I'm focused on 45. 45 being the address portion of the host. All right, my block size is 256 minus 224, which is equal to 32. And then I can start writing out my networks. 109.76.0.0, 109.76.32.0, 109.76.64.0, 109.76.96.0, 109.76.128.0, 109.76.160.0, 109.76.192.0, 109.76.224.0, and then if I were to add another one, it would be 256.0, so that doesn't exist. So we've actually written down all of our networks, all right? Because 224 plus 32 is 256. You can't have a 256, so, all right? Do you understand how I got number one? The 225, or 255, 255, 224. Maybe you can't do it quickly in your head, but do you at least understand mathematically the principle between a /19 equals 255, 255, 224.0? Because that's 19 ones, right? /19. Do you understand that I said we're subnetted in the third octet? And you understand why I put 45 down? Because I am trying to calculate the network ID, broadcast ID for that host, for that address. All right, so I'm just kind of calling my attention to the 45 because that's what matters. Do you understand where I got the 256 minus 224 for my block size? Yes? And do you understand how I got each of these networks? We're subnetted in the third octet. I'm adding the block size each time because every number in the third octet divisible by the block size is a network ID. So what network does this client belong to? This network, right. And what is the broadcast for that network? 109, 76, 63, 255. That is the last address before the next network. And then what is the host range? 32.1 through 63.254. Does that make sense? Takes a little bit of practice. The nice thing about this, though, is it breaks down subnetting to one octet. You're just focused on a single octet, and you're doing these 4 calculations each time. And eventually you get to the point where you can pretty much just write any address, 78.54.99 slash, even if I did like slash 12, okay? Now I'm subnetted in the second octet. Slash 12 is a 240, which is a block of 16. The closest thing to 78 divisible by 16 is, well, that you have to might do a little bit of math, right? I know that 96 is divisible by 16. I know 64 is divisible by 16. 64 plus 16 is 80, right? So the network ID is 64. Well, it can't be 64, can it? It has to be lower, doesn't it? So it would be 48, wouldn't it? 48 is divisible by 16. So 10.78, sorry, forget it. I was mixing the third and the fourth. 78 is higher than 64, so it is definitely 64, right? So the network ID would be 10.64.0.0. The next network is 10.96.0.0. I mean, sorry, 10.80.0.0. This is what happens when you don't write it down. And so that means that the broadcast would be 10.79.255.255. Let's go ahead and write it down. So 255.240.0.0, that is the second octet, right? 256 minus 240 equals 16. Equals 16. So the first network is 10.0.0.0, 10.16.0.0, 10.32.0.0, 10.48.0.0, 10.64.0.0, 10.80.0.0, 10.96.0.0, and so on. 78 is before 80, but after 64. So this is the network ID. And 10.79.255.255 would be the broadcast ID. And then the host range would be 64.0.1 through 79.255.254. Make sense? Is it kind of making more sense as you do a couple more? The nice thing is this method works. It doesn't matter what the address is. It doesn't matter what the mask is. All that matters is you follow the same 4 steps. What is the block size? What octet am I subnetted in? Write out the networks based on that block size. Okay? All right. In the interest of kind of moving forward here, we will continue on. They go through a couple of different calculations. Obviously, in this particular case, it's a very easy calculation, isn't it? The network ID is 192.168.52. Because all the ones, this is what we would refer to as kind of subnetting to a major boundary, even though this is actually technically not even a subnet, because 192 is originally class C, but you get the idea. Here we borrowed a 1, which means we went into the 4th octet, which means that only the last 7 bits are now the host portion, and the first 25 bits are the network portion. All right? So each time you borrow a bit, you're creating twice as many networks. This is the formula, right? Remember we said the subnet formula was 2 to the power of n equals subnets? We borrowed 1, that's 2 subnets. If I borrow 2 bits, that's 4 subnets, and so on. So the book is going through the same calculations that we did. I just kind of try to do it in one concise discussion, right? The formula to determine the number of hosts per subnet is 2 to the power of n minus 2. But again, this power, this exponent, is the number of zeros, not the number of ones. Zeros always represent the host. Ones always represent the network. So 1 borrowed bit for networks, 7 bits left over for hosts. That means 2 subnets at 126 hosts per subnet. All right, here they borrowed additional ones. Now they've gone down to a slash 29, right? 24, 25, 26, 27, 28, 29. So now we borrowed 5 bits for the network, which leaves us only 3 bits for hosts. Every time you borrow additional bits, you're creating smaller networks. And it works exactly the same way for IPv6. The more bits you borrow, the smaller the network is. All right? So we have a Class B subnet here. This is the classful representation. 172 is a Class B address. The normal mask is a /16. Here they borrowed 5 ones, actually 6 ones in this case. So they went from a /16 to a /22. 2 to the power of 6 is 64 subnets. And then that leaves us this many bits for hosts, which is 10. 2 to the power of 10 is 512 minus 2 is 510 hosts per subnet. All right? Class A, same way. We just have more bits that we can borrow with Class A. A Class A address is normally a /8, which gives us 24 zeros to play with. So we can create a lot more subnets with a Class A address than we would with, say, a Class B or a Class C address. All right? How do I determine the addressing scheme? Again, this depends on how the addresses are allocated. Going back to our original diagram here, right? We said we were going to go to a /26, which is 255, 255, 255, 192. That's supposed to be a 5. 192, 256 minus 192 is equal to 64. So my first network would be 10.0. My next network would be 10.64. My next network would be 10.128. And my last network would be 10.192. And then all I do is I take those networks and I assign them to the interfaces. And that's how it basically works. All right, this is simple subnetting. In this particular case, we're subnetting using common masks, so every network is the same size. What happens if the networks are not the same size? Well, they aren't technically the same size in this case. We could actually do something called Vlsm in this case, or variable length subnet masking. We'll talk about that a little bit later on. All right? But calculating the anatomy of a subnet is really, really important because you need to know where the network begins, where the network ends, and what usable addresses exist within that address space. All right? It says here, if a network address is subnetted, the first subnet that's obtained after subnetting the network address is called subnet 0. because all of the subnet bits are 0. To determine the subsequent addresses, increase the subnet addresses by the bit value for the last bit that you borrowed. That is a very fancy way of saying block size, which is kind of interesting if you think about it, because that's actually another way of looking at it. The value of that bit allows us to determine what the block size is. We can, well, this is on a major boundary, so it's not really, doesn't really apply in this case. But let's say, for example, going back to this example, a 192 is 128 plus 64. Well, that's our block size, isn't it? So they're telling you the same thing that I told you, which is figure out the first network is always going to be 0, and then every network after that is going to be an increment of the block size. All right? And that's basically what they're saying. And that's literally what they're saying in this particular case. All right? I know it's a lot of information, and it does take a little bit of practice to kind of get used to everything. Here's the blocks that they're creating. So 0, 1, 2, 3, 4, 5. In this case, the value of this bit is 1, right? But actually, if we were to do our calculation, the calculation that I showed you, it's 256 minus 255, really. 256 minus 255 is 1. It's the same thing. So we're still doing it based on block size. Okay? Notice that the addresses of the subnet has all of the host bits set to 0. This address is one of the reserved addresses in the subnet. In other words, it's the network ID. The other reserved address in the subnet is the directed broadcast address, where all the bits are set to 1. The last address in the subnet, where all the host bits are set to 1. Not the network bits, but all the host bits. All right? So they're just kind of breaking down the anatomy of their subnet. Here's the first network, second network, third network, fourth network. If this network starts at 1, then the previous network ends at 255 in the fourth octet. This network starts at 2, then this network ends at 1, 255, 255, 255, and so on. All right? It takes a lot of getting used to, because, again, there's a lot of different ways to kind of look at this and to calculate these values. There's never, I mean, certainly the only way that really matters is the way that gets the right answer. But like I said, there's several different ways that you can actually do these individual calculations. All right? All right. So in this particular case, we went to 2 bits in the third octet. The value of this bit here is 64, which means our blocks are 64. And if I start at 0, the next network is 64. The next network is 128, and so on. All right? 0, 64, 128, 192. We're just adding that block size over and over again. As long as you know what octet you're in. You always have to pay attention to the octet you're in, because that's going to change how the calculations are done. And then one more example they go through here. In this case, actually, let me just grab this table real quick. So 0, 64, 128, 63, 255 is the address before 64. 127, 255 is the address before 128. 191, 255 is the address before 192, and so on. All right. Here's another example. We started with a, well, what appears to be a Class C address, but we've subnetted all the way down to the fourth octet. The value of this bit is 32, which means we have blocks of 32. But if you take 256 minus 224, you get 32. So the first network is 0. The second network is 32. The third network is 64, and so on. There's our networks. 0, 32, 64, 96, 128, 160. Just adding 32 each time until I finally get to the final network, which is the 255 subnet. All right? Any questions? Another benefit of the ability to do subnetting is the ability to do variable length subnet masking. So far, what we've talked about up to this point has all been common subnetting, where basically we're taking a network and we're dividing it up into equal pieces. And that sounds ideal, and in a lot of cases that works just fine, but there are instances where we might have to take an actual network and we might have to break it up unevenly. Maybe one particular part of the network has 150 clients, and another network has 500 clients, and another part of the network has 1,200 clients, and so on. So we don't necessarily want to take the same network and then end up dividing that up equally, because then we're going to end up wasting a lot of address space, because we would have to say, for example, create a common subnet that supports 1,200 and something clients, and apply that same subnet to maybe a network that only has 150 clients or something like that. So variable length subnet masking is the concept of taking a block of addresses and then dividing that block of addresses up into unequal pieces and then applying those pieces as necessary. So for example, if you look at this diagram, the first network has 19 hosts, the second network has 28 hosts, the third network has 28 hosts, and then we have a couple of point-to-point links in between. So it doesn't make a whole lot of sense, excuse me, especially on the point-to-point links to assign a /24 to those particular subnets. We could do that, and frankly, if we're using private addressing, meaning not globally routable addresses that are more difficult to come across, doing common subnetting is not really that big of a deal. But again, we may decide that we want to plan out our network resources so that we apply the subnets in kind of a more appropriate fashion based on the size of the subnets themselves. So maybe a /30 subnet mask would be a more appropriate for those point-to-point links between the HQ routers and the branch routers. And then the network with the 19 hosts, we would want maybe a block of 32 addresses for that network, so that would be a /27. And then for the 28 hosts, again, another block of 32, so that would be a /27. And then the final block of 28 hosts, that would be a /27, and so on. And generally, that's kind of how we consider it. We always consider the size of the networks based on the block size that we need to create those subnets. It makes sense, right? I mean, if we have 60 hosts, maybe a block of 64 is going to be adequate. If we have 100 hosts, maybe a block of 128 is going to be adequate. The challenge comes, though, is how do we actually assign those addresses? How do we take one network and then start to divide up that network, because then we have to be able to identify where those networks begin, where those networks end, and so on. And again, that can be a little bit more challenging. Here you can see, for example, we have our address allocation is kind of more representative of what would be appropriate in this particular case, because we've got a /30 for this link, a /30 for this link, a /30 for this link, and then we have our /27s for these networks here. And again, it makes logical sense to do it that way. The challenge is, like I said, how do we figure or how do we calculate what those specific networks are going to look like? In other words, where do the networks begin? Where do the networks end? How do we divide up those networks? So I'm going to show you guys kind of a visual way of doing this, of allocating these network resources that doesn't require you to do a whole lot of mathematical calculations. Let's say, for example, we have a network here. Let me change my color. We've got a network here, and we have maybe 100 hosts here, and we have 230 hosts here, and we have maybe 120 hosts here, and we have 450 hosts here. All right, and I was given the network block of 10.10.00/16. All right, so what I would do in this particular case is I'd say, okay, how could I allocate address space to each of these blocks, identify where the networks begin and where the networks end, and you could do it mathematically or you could do it visually. So let's do it visually. Let's take our third octet. We'll draw a circle that represents the third octet, and that's going to go from 0 to 255. And then I'm going to draw a circle that represents the fourth octet, 0 to 255. All right, so those circles represent, in essence, the networks that we're trying to create. And what we do is we divide these circles, and by dividing those circles, we're creating the actual subnets. There's one rule that you have to follow, though, when you're dividing the circles. You have to divide pieces by half. You can't take a piece like that and then allocate that address space and then leave the rest by itself. You always have to divide by half. All right, so let's say, for example, this would be a /16. When I divide this, this becomes a /17, and this becomes a /17. In fact, each time I divide the network, I'm borrowing an additional bit, which means I'm creating more subnets, but I'm also making the subnets smaller. So this would be subnet number 1, which would go from 0 to 127. And this would be subnet number 2, which would go from 128 to 255. But watch how this works. How many addresses, how many host addresses exist in those blocks? I could do the math, right? I could say number of zeros in the mask, which is basically 15 zeros in the mask, to the power 15 minus 2. Or I could say, well, this is 128, and this is 256. So if I take 128 times 256, it's 32,768 addresses. Because that's essentially how we would assign the addresses, right? 0.0, 0.1, 0.2, 0.3, 0.4, 0.5, you get the idea. Well, certainly 32,000 addresses is going to be way too much. So what we're going to do is we're going to divide this again. I probably should have started with a different example, but I wanted to really kind of give you the idea. Let me do it this way, actually. I wanted to kind of give you an idea of visually how we could divide this up. All right, so let's say now this is divided again, and now it becomes /18. So this is still a /17. This is a /18. Because again, each time you divide a piece, you're borrowing an additional bit. So that is now 64 times 256. It's a little smaller, but it's still too many addresses. If I divide it again, /19, right? If I divide it again, /20, and so on. You get the idea. Now, if I need 120 addresses, technically, I really only need half of this circle, don't I? So this is why I should have probably started with a different number, because I've got to basically divide these down into pretty small increments. So here's what I'm going to do. Let me try and do it this way. Let's make this pen a little bit thinner. So 0 to 255, there's my /17, there's my /18, there's my /19, there's my /20, which is, by the way, a block of 16. This is a block of 32. That's a block of 64. That's a block of 128, right? So, and if I divide this again, that goes down to a /21. That's now a block of 8, and so on. So for 450, I would need how big of a block in the third octet to be able to handle 450 addresses? 2, right? 256 plus 256 is 512. So this is down to a block of 8, and then I would divide it again to a /22. That would be a block of 4. Divide those pieces again. You get the idea, right? And then all I would simply do, let me actually just do this. Let me come up with an easier one to do, even though the concept is still the same. Let's do something a little bit easier so we don't have to divide it up as much. Let's take the same network here, but now we have 4,100 hosts. Here we have 5,030 hosts. Here we have 6,200 hosts. And here we have 4,500 hosts. Okay, same concept. This circle represents the third octet. This circle represents the fourth octet, 0 to 255. So we divide /17, /17, divide it again, /18. Now, if I take 5,000, let's do the largest one first, 6,200, and I divide that by 256, that's 24, well, round it up, 25 times around, right? So that would be a block of 32, actually, that I would require for the 6,200 hosts. So that makes it a little bit easier, /19 and /19. So here's my first block of 32. I would take that network and I would assign that network to that interface. So the address or the network here would be 10.10.0.0/19. But now I've allocated that piece of the pie. I don't have to worry about that anymore. That piece has been allocated, it's done, it's used. I can now deal with these other remaining pieces. All right? What about 5030? 5030 divided by 256 is 19. So again, we're going to have another block of 32, aren't we? All right? Because we can only do blocks of 1, 2, 4, 8, 16, 32, 64. So this block of 32 would then get allocated to this network. All right? If this is a block of 32, that means it ends at 31, and this one starts at 32. So this would be network 10.10.32.0. Getting a little hard to write here. 32.0/19. You get the idea. All right. Now, if I take 4,500, divide it by 256, that's 17. So again, that's going to require a block of 32. Then I can come down here and divide this. This would be /19s. That would be a 64. That would be a 96. And I can allocate that block over here. And I can allocate this block over here. You get the idea. It starts to end up looking like this is common subnetting, though, because every one of those blocks is the same size. But the point is, we're allocating blocks visually. We're not using math necessarily. I'm kind of just using almost like a pizza idea, right? I'm slicing up the pieces of pizza, but I can only divide pieces in half. And that allows me to allocate specific sizes of networks to specific places in the network. This whole concept is called variable length subnet masking. It allows us the ability to apply different subnet masks in different parts of the network based on whatever the size of our network is, and that's how we allocate the addresses. Let's actually look at the example they have in the book here. Oops. They've got an example here. It says implementing Vlsm. I was given a 172.16.32.0/20 subnet. 32.0/20 subnet, and I have 50 hosts in each of the LANs. Now, automatically in your head, you're thinking, okay, if I have 50 hosts, how big of a block do I need? Right? If I have 50 hosts in each subnet, how big of a block do I need to be able to allocate addresses to that network? I need a block of 64. All right, specifically a block of 64 in the 4th octet, because we're only dealing with 50 hosts. We know that we're in the 4th octet. So let's do a little math here. 256 minus 64 is what? Well, actually, let's do it this way. A block of 64, now we could do it that way. 256 minus 64, what is that value? 192, right? Which basically means that's the mask portion. That's what my mask becomes in the 4th octet. So I'm going to apply a mask of 255.255.255.192, which ends up being a /26. Does that make sense? But that's a /26 for each of those separate networks on the right, because they're 50 hosts each. Let's see if that's what they came up with in this particular case. And again, we didn't really do any hard math. We were just saying, okay, how many, what are the block sizes that we're dealing with? In this case, we're dealing with block sizes of 64. So it says here, the next figure shows in binary the original subnet of the 172.16. There's a lot of typos here. 172.16.0.0/16 network to /20 by borrowing 4 bits, which provides 16 subnets, which is true because we borrowed 4 bits. 2 to the power of 4 is 16, which also, by the way, leaves us 12 bits over for zeros, and 2 to the power of 12 is 4,096 minus 2 gives us 4,094 hosts per subnet. All right? But we should really borrow further so that we can increase the number of subnets and get closer to the desired number of hosts per subnet. So borrowing an additional 6 bits results in an additional 2 to the power of 5 subnets, which is 64 subnets. That leaves us 6 host bits, which is 62 hosts per subnet. Or 62 addresses, 64 addresses, but 62 host addresses per subnet. Wouldn't it have just been simpler to say, okay, what block size do I need? I mean, that was a pretty complicated way of deciding that we're going to need 62 addresses per subnet. You know, if you think in block size, it makes your life a little bit simpler. If it was 20 hosts, I could do a block of 32. If it's 8 hosts, I do a block of 16. If it's 50 hosts, I do a block of 64, and so on. And then I can just simply calculate what my mask is going to be based on that. So this was the original subnet that was created, the /20, which is the 255.255.240. But again, that creates, a decent number of subnets. We certainly have enough subnets to meet our requirement, but we're wasting a lot of address space because we're assigning 4,094 addresses per subnet. So borrowing those additional bits creates those additional subnets, and it gets us to where we need to be. All right? Because we're dealing with blocks of 64, actually, in this case, we're dealing with, blocks of 64. We can now write down what each of our subnets are, starting at 0 and then we can start to allocate those address blocks to where they need to go. So the first network would be 32.0, the second network would be 32.64, the third network would be 32.128, 32.192, 33.0, and so on. We can just keep assigning the address blocks as needed until we've assigned or allocated all the addresses. This doesn't really depict Vlsm though, does it? Not really, because all the networks happen to be the same size. All right, but let's expand on that, right? Because not only do we need to have the networks for the hosts themselves, we also need to have the point-to-point links have addresses as well. All right, if I have a block of 32, and I'm going to decide to further divide a block of 32 into blocks of 4, how many subnets can I create by doing that? Well, if I do the math, 32 divided by 4 is 8 subnets. So I can actually take one of those blocks of 32 and divide that 8 times to create networks of 4 addresses each. So if we look at the diagram, we started at 0, we went to 64, we went to 128, we went to 192, but which block is left over? The last block of 64, right? 32.193 to 32, well, actually that's already allocated here, isn't it? So we would have to go up to our 33. We do have 33 available, by the way, because it's a /20 originally, so we can go all the way up, beyond 33, actually. /20 is a block of 16 starting at 32, so we can go all the way up to 47, actually, from 32 to 47. Based on the original number, we can go from 32 to 47. So maybe I just take the 33 block, and instead of allocating the 33 networks as /26s, I start at 33 and I start breaking those down into /30s. All right, so 33.0/30, 33.4/30, 33.8/30, and so on. And that's most likely what they're going to do in this particular case. To calculate the subnet addresses for the WAN links, further subnetting of one of the unused /26 subnets with a 30-bit mask could be done. All right? For example, the 33.0 subnet, which would be logically the next subnet available, because again, we started with a /20 and we went all the way down to a /26. So we could have made them all /26s if we wanted to. All right? So we borrow an additional 4 subnet bits. That's going to give us an additional 16 subnets, and that's going to leave 2 host bits. Because we went from a 26 to a 30, that leaves 2 bits left over as zeros, and 2 to the power of 2 is 4. But remember, you have to subtract 2 because you have to count for the network ID and the broadcast ID. So that's perfect. Then we just start allocating those subnets. So we're taking this, the next logical 33.0/26 subnet, and we're dividing it in based on /30. All right, so there's 33.0, 33.4, 33.8, 33.12. Think about it though, would we technically need to create all the way up to 33.60? Not necessarily, right? Because if you think about it, you look at the diagram here, we need 4 of those networks. We need 4 of those /30 networks. So let's go back here and let me just draw a circle and show you what I mean by that, right? So here's, I guess, logically what we would have created. These are my blocks of 64. Starting at, what was it, 172.16.33.0, right? So that's what we started with, 172.16.33.0. Let me write that again because it's kind of messy there. 172.16.33.0. So there's my .0, there's my 64, there's my 128, and there's my 192. Okay? So what they were saying is, let's go ahead and just do this across the whole /64. Let's just divide it up into addresses of 4 for each. But actually, I only need four point-to-point links. So if I divide this, this becomes a block of 32. This becomes a block of 32, which means now we went from a /26 to a /27. Right? The whole circle is 24. This is 25. This is 26. This is 27. So that's a /27. That's a /27. All right? But the address range is from 0 to 31, which is 32 addresses, isn't it? If I divide that again, now we have blocks of 16. If I divide it again, now I have blocks of 8. And if I divide those two pieces again, then I get my blocks of 4, 4, 4, and 4. You see what I'm saying? It's really hard to draw here because it's so small. But my point is that you don't have to take this whole 64 block and make them all networks of 4 addresses. As long as I can have enough to meet this requirement, which is 4 point-to-point links, I can do this, right? I'm going to draw it one more time because I really want you guys to get this point here. There's my /64s. There's my 32. There's my 16. There's my 8s. And then there's my 4s. So 1, 2, 3, 4 subnets. So I take those 4 subnets and I allocate them to those point-to-point links, which leaves me the 16 left over. It leaves me the 32 left over. And it leaves me the 64 left over. And in reality, I don't even really have to divide this piece. I can leave this piece as a 128. And then later on, if I need to use those pieces for something else, I can either divide them or I can just assign them. What I can't do is I can't join them together. There's no way that you could make this block consecutive. There's no way that you could put those two pieces together. So because if I want to create these networks, I have to create these networks. I don't have a choice. You guys following what I'm putting down here?
Yeah.
All right. I know it's a lot of information, and it takes a lot of practice. Variable link subnet masking is more difficult because, again, you're not applying the same subnet mask across the entire network. So it's a little bit more challenging, but if you look at it from a visual perspective, it makes it a little bit easier to understand, I think. Maybe. It makes perfect sense to me, but I've only been doing this for eons. All right? The takeaway, of course, is that we don't have to apply the same subnet mask to every single network in our enterprise. Now, we haven't really talked about this, but in most modern enterprise networks, we're using private addressing anyway, what we call RFC 1918 address space. Private addressing is just basically addresses that are not routable on the internet. And we can use them however we want internally. So do we really care about conserving address space if we're using private addressing? No. Because we can just use those networks however we want. So I may decide, you know what, I don't care that I only need 2 addresses for those links. I'm just going to go ahead and assign every network as a /26 because I want to make my life easy and I want every subnet to look the same. doesn't really matter. It's not that the network is going to operate less efficient if I allocate a larger block of addresses to that network. It's still going to operate the same way it's designed to operate, which is how many hosts are actually physically on the network. And then based on that, that's how I'm going to allocate, or that's how the network is going to get its efficiency, is based on the number of actual hosts, not what I've allocated to that particular network. All right? All right. So they get your fours. We only had to create, technically, those 4 networks, 0, 4, 8, and 12. We could have left the 16 by itself as a block of 16, and then we could have left the 32 block going from 32 to 63 as its own block, and so on. All right? All right. Private versus public. There was another RFC that was written. It's called RFC 1918. RFC 1918, which is allocating address allocation for private internets. This came out in 1996. So CIDR, the classless interdomain routing RFC, came out in 1993. This one came out in 1996. These were the folks that got together and kind of developed it. One person from Cisco, another person from Chrysler, another person from the Europe Regional Internet Registry, De Groot from the Regional Internet Registry, and then Mr. Lear from Silicon Graphics. I remember that company. I don't know if they're still around or not, but we used to deploy Silicon Graphics computers at one point. But anyway, RFC 1918 said, you know what? And by the way, all these RFCs, we'll talk about network address translation a little bit later on as well, which is necessary if we're going to run private addressing. But all these concepts of classless interdomain routing, using private addressing, and so on, those things came about because we were running out of V4 address space. It was being depleted far too quickly. And everybody realized very quickly, well, this address space is just not simply not large enough to meet our requirements. So we need to come up with some other ways of utilizing this address space. So one of the things that they did is they said, let's go ahead and take particular pieces of the IPv4 address space, and let's allocate those as private address spaces, all right? Meaning that these are network addresses that you can use internally however you like, but you cannot use them on the internet, all right? You guys are familiar with this. I mean, you've seen this address space many times. The 10 block, the 172.16/12 block, and the 192.168/16 block are all private addresses, right? So hosts that are publicly accessible over the internet require a public IP address. Internet stability, another typo, internet stability depends directly on the uniqueness of a public IP address. Sure it does, right? Every client that's communicating on the internet is going to have a private address. Internet, yeah. All right? It says internet, but anyway. So we have to have a mechanism to ensure that the addresses are unique. And originally the idea was, let's just go ahead and just allocate everybody a public IP address. All right? But the problem is they were just running out of address space. There just wasn't enough address space to go around. All right? So what they did is, these are the public ranges. These are the public ranges of addresses. But what they did is they said, you know what? Let's go ahead and allocate specific blocks of addresses as private. In the Class A space, it's the entire 10 range. So any address that starts with 10 is considered private. In the Class B space, the entire 172.16 to 172.31 address space. And then in the Class C space, the entire 192 to 168 address space. It's not that these addresses are treated differently. These particular blocks of addresses work just like any other address that you use. The only difference is these blocks of addresses are not routed on the internet. So if you want to go to the internet using these address spaces, you would have to do some sort of network address translation. All right? I just skipped over some stuff. I want to make sure we go back and take a look at this. These would then conversely be the public ranges, anything that's outside of those address blocks that we just saw. And the regional internet registries, we talked about this earlier. There's 5 regional internet registries: Africa, the African Network Information Center, AFRINIC, the Asia Pacific Network Information Center, the American Registry for Internet Numbers, Latin America and Caribbean Network Information Center, and RESO IP, European Network Coordination Center. That's probably not how you say that, but whatever, okay? We'll just call it RIPE, all right? So we talked about how the IANA allocates address spaces to these particular regional internet registries, and then those regional internet registries allocate address space to their customers, the service providers, and so on. With the rapid growth of the internet, public v4 addresses started to run out. Actually, it happened relatively quickly. I mean, if you think about it, go back to the list and we do a quick Google search on the IANA IPv4 registry, and we look at when the first block of addresses was assigned, that was in 1991, okay? Well, when did CIDR come out? 1993. When did private addressing come out? 1996. So we're talking about within a 3 to 5 year period, they were already scrambling to come up with new ways of allocating address space because they knew that they were going to run out of address space. Now, technically, the address space was actually created in 1981. In fact, specifically September of 1981. But it wasn't until 1991 that we had this architecture in place to start allocating addresses in an organized fashion. All right. Subsequently, you could also look at the v6 global unicast address space. Remind me later. IPv6 global unicast address space. And we can see when the first v6 address was allocated. This is how the addresses are broken down. We'll talk about that a little bit later on. But it wasn't, it was in 1999 was the first block of addresses that was designated in IPv6. That was IANA, but actually in July 1st of 1999, Asia Pacific got a prefix, ARIN got a prefix, RIPE got a prefix. We came up with some 6-to-4 tunneling in 2001. So IPv6 has been around for a while, okay? When was the last prefix assigned? November 6th of 2019 was the last time that a global v6 prefix was allocated. So we haven't talked about the size and scope of IPv6. We'll talk about that later on. It's pretty amazing. It's actually pretty astronomical. It's pretty amazing how large that address space is. It's pretty crazy, okay? We'll talk about that a little bit later on. All right? So in February of 1996, the IETF published RFC 1918, Address Allocation for Private Internets. And again, the whole concept here was, hey, let's go ahead and set up these blocks of addresses that anybody can use any way they want. They can subnet them, they can apply addresses in different ways, but anybody can use these addresses any way they want. But the only restriction is that these blocks of addresses will not be routable on the internet. They're routable internally, but they're not routable on the internet. So if you want to use these private addresses internally and then you want to go to the internet, you have to implement something called network address translation. And we'll talk about NAT a little bit later on. Even NAT didn't exist originally. NAT was developed after the fact, right? It wasn't even necessary. NAT wasn't even necessary until we started allocating private address blocks. All right? We also talked about some of the reserved address space, certainly the network address, which is always the very first address within a block. That represents the network in routing tables, in databases and whatnot, allows us to identify the network ID, if you will, of a particular network. The broadcast address is a way for me to communicate to all the clients within a particular subnet. Now, there are two types of broadcasts. There's the all ones broadcast, which is kind of like a generic broadcast regardless of what network you belong to. And then there's what we call a subnet directed broadcast, which is the broadcast address for the individual subnet, which is the very last address within that network range. This particular broadcast address is used primarily in scenarios where I don't know what subnet I belong to. If I don't, like for example, DHCP, a DHCP discover, I'm trying to determine what my address is. I don't know my address in mask. How can I do a subnet directed broadcast if I don't even know what my own address in mask is? But I still have to have a way of communicating, and this all ones broadcast is the way that we do that. It doesn't mean, by the way, that this is routable. Just because it's not directed to a particular subnet does not mean that it goes beyond the router. It still stops at the router. Always routers drop broadcasts, whether they're subnet directed broadcasts or whether they're the all ones broadcast, routers never ever forward broadcast packets. The directed broadcast address would be the broadcast address that's specific to a particular subnet. And again, this is always the very last address within the subnet scope. The first address is the network ID. The very last address is the broadcast ID. All right? We do have some other addresses as well that are allocated for special use. One of those would be our loopback address. We talked about that. Anything pretty much within the 127 range. People always kind of mention 127.0.0.1 as a predictable loopback IP, but the reality is it's any address within the 127 scope is going to perform the same function. Again, what are we testing when we ping that address? We're looking for a reply, and a reply to that ping indicates what? That the software is working on the computer. It's not testing my local physical interface. It's not testing connectivity to the local LAN. It's literally testing the software stack. Remember, back in the day, we used to have to install the protocol stack separately from the operating system. So we had to have a way of testing the protocol stack to make sure that it was functional. And then we could then go on and test our network interface card and so on. Another type of address is something called an auto configuration v4 address, what some people affectionately refer to as an APIPA address, right? Automatic private IP addressing. Typically, this is a specific block. It's 169.254/16, all right? And it's a specific block of addresses, but it is used for things like diskless workstations. So maybe I have a computer that doesn't have a hard drive. It has maybe some flash memory or some local memory. And so if it doesn't have a hard drive, it most likely doesn't have an operating system, but it has enough resources to be able to boot up, attach itself to a network, give itself a 169.254 address, and then go out and search for a network server that it can load an operating system from. Typically, though, when we see this 169.254 address, it just simply means that we weren't able to allocate an address to ourselves, and so the client basically gave itself this address to see if it could participate in the network, right? In fact, they say that here. You'll mostly see this address as a failure condition when the PC fails to get an address through DHCP, okay? That wasn't its intentional purpose. The intention of this address was to allow computers like diskless workstations to be able to assign themselves an address, go out on the network, search for, in that same subnet range, search for a computer that it can attach itself to so that it can load operating system and then start communicating. All right. Another special case set of addresses is the documentation block, which is kind of interesting. A lot of people aren't aware that this exists, but 198.51.100.0/24 reserved for documentation. So for like training documents and stuff, if you want to put in a quote unquote, it's almost like the idea of the 555 extension, the 555 prefix. When you see people dialing phone numbers on TV, and they're always putting in 555 something, because that 555 prefix was used for that purpose, so that people weren't actually putting in real phone numbers. And so this is the same kind of concept, all right? They don't legitimately appear in the internet, and they actually can be used, even though we would use them for documentation. They can actually be allocated as well, but they're not routed on the internet. So they're almost like private addresses, but you should pretty much avoid using these because these addresses end up showing up in a lot of documentation. All right. Then we have the all zeros address, which is 0.0.0.0. That means one of two things. It either means this host or locally originated, or it means that the device simply doesn't have an address. In the case of DHCP, this would be used as the filler for the source address during the DHCP discover process. Because I'm trying to figure out what my address is supposed to be. But I still have to build the PDU appropriately so that I can generate the DHCP discover and go through the DHCP process. All right? The last section here, pretty straightforward. How do I verify addresses on a host? I'm not going to spend a lot of time on this. You guys are probably familiar with most of this. You can use the, in the PC, you can use the ipconfig option, or you can use the network connections configuration screen and under properties. On a Apple Mac, same thing, TCP IP tab under system preferences and network, or we can use an ifconfig in the command line or terminal application. On a Linux host, we use ifconfig as well. There's also some GUI options too. Or we can use manual commands, man ifconfig, and so on. All right. So that concludes section number 7. We finally made it through. I think that was about a 3-hour section, so that's good. All right. We'll see you guys in section 8.